I hope that those online can be in person in some future events. So thanks everyone for joining. I think you for sure make this a great meeting. So some practical informations. João will be the chair of the next session, so I'll pass on the microphone to him. We have the pre-recorded talks. Everyone that had pre-recorded talks, they are already available. Those speakers that have not yet sent their presentation, I think there's only one. Please send us your presentation. And I think we are ready to go. So in the interest of time, I have 3 minutes. So my idea was to be quick. So yes, what else? Well, I would like to thank CBPF for the great infrastructure for hosting this event. Thanks to this institution, we have very easy hybrid events. So we take this opportunity. Unfortunately, this time we didn't have any funding to support people coming here, but at least we can support the online participants. So most of the participants are from Brazil, but as we may have some foreign participants, and of course, as English is the language of science, either we like it or not, that doesn't matter. So we suggest people to present in English, but if you don't feel comfortable, yes, you can present in Portuguese, no problem. So first speaker of today is Carlos Melo, but we'll wait 2 minutes so that we don't start ahead of time if someone is connecting. As we told before, these talks are recorded. Everyone that's giving talks agreed with their talk being recorded, but if this is not the case, please let us know. Also, if you don't want to be on tape, just look for a blind spot in our cameras, and you can always free to ask questions through Slack, and the questions through Slack are not recorded. Our discussion sessions, we may sometimes touch in interesting issues that maybe people don't want to be on tape. So of course, we may also do not record if we believe it's not. We want to have really open discussions. The idea of this meeting is a really workshop. So it's not like just a meeting to present the results. Of course, we want to people show what they're working on. So that's why we have talks. But the talks, the end goal of the talks is to make people talk among each other, right? Know what everybody's doing so that we can interact. So the whole infrastructure we are setting up is to maximize these interactions. So that's why I'm saying that if you don't feel comfortable, for some reason, we will not record, for example, the discussions and so on. So that really there is a lot of freedom of speech, really, to present any kind of discussion, ideas, and so on. And of course, the second part of the meeting is even less formal. So this first part, today, tomorrow, we have talks. We have time for questions. 15 minutes for the talks, 5 minutes for the questions in each talk, but then 20 minutes discussion sessions to have a lot of time to ask more and more questions. We have a fully open discussion session also in each period, in morning, afternoon. These are fully open. We have some suggestions of subjects if we lack ideas to discuss. So really the ideas to discuss. And again, the second part of the meeting, May 2 and 3rd, is even more open. There are some hands-on sessions. We have 2 hands-on sessions on Thursday and 3 hands-on sessions on Thursday and full discussion on Friday. And whoever wants to propose any specific discussion, any focus discussion, if they want to sit around with 2 collaborators, 1 online, 1 sitting there, we have rooms for that. So that's the idea. Really workshop. If you want to sit and work, profit from the fact that we always are busy, but we have reserved this time for this workshop. So you can just ask for a meeting room independently of the number of people you want to get together with. If it's in parallel to another activity going on the second part of the event, there's no problem. We want really to maximize interaction. So yes, we have a program for the second part as well, but feel free to do anything, and we guarantee you have time and some remote connection, okay? So that's the idea. I think I already talked too much. It's 9:01. So Carlos, the floor is yours, and João, the microphone is yours. Hi, Carlos.
Hello.
Can you try to share your screen?
Yeah, just make sure you can see now, right?
Yeah, but you can see in the full screen mode. Yeah.
Yeah, so in full screen.
You can begin whenever you are.
So just first of all, I would like to thank the organization for giving me this opportunity to talk about my work, and also for organizing this third meeting of LEGAC, which is uh, always great to be part of. So my name is Carlos. I'm a PhD student in Brazil, in Porto Alegre, supervised by Professor Cristina Forlaneto and Ana Quinha Santos. But I'm also doing a 6-month visit in Portsmouth and being supervised by Professor Thomas Collett. And today I will be talking about self-consistent modeling of strong gravitational lensing and stellar dynamics. So just to give some motivations and an overview, I'm most interested in early type galaxies, which are commonly defined as gravitationally bound systems composed of stars, planets, gas, and something that we call dark matter. The systems are typically old and red, and we understand these ETGs as the end product of galaxy formation and evolution. And the interesting about the systems is that they share a lot of many scaling relations that are connected to their mass profile. And just to give an example, we have this thing called bulge halo conspiracy, where the total mass density profile of ATGs seems to follow a power law distribution. Even that the individual contributions, like the stellar mass and the dark matter mass profiles, doesn't necessarily follow a power law distribution. And other interesting thing about this is that the slope of this power law distribution seems to be very near the isothermal value, I mean the value of 2. So in this plot, we are seeing the evolution of the slope of a power law mass profile as a function of the redshift for the TNG simulation. And as you can see, we see a little no evolution for redshift below 1, and some evolution or some changes in the redshifts above 1. So tracking the mass profile, we can study how this galaxy evolves. But not only that, the mass distribution can be used to do a lot of other things, like IMF calibrations and also gravity probes. And the way we measure the mass distribution is very important, and we have different methods to do that. And in particular, I'm interested in these 2 different methods. One is the gravitational lensing, and another is the stellar dynamics, because these 2 methods are complementary in a certain way, such that we can combine these 2 methods self-consistently to break intrinsic degeneracies to the methods, which we are not able to break with the individual methods. Like in the strong gravitational lensing, we have the mass sheet degeneracy, and in the stellar dynamics, we have the mass anisotropy degeneracy. And these 2 issues are really hard to break if you not combine these 2 methods. So the goals of this work and presentation is combine 2 different traces, strong gravitational lensing and stellar dynamics, to reduce the degeneracies in the inference of the mass profile, and provide some insights into the bias and the advantages of this combined method. And also develop a tool or a code to make this self-consistent modeling straightforward and user-friendly. So the overall framework that we require is that we need to parameterize the mass distribution of the galaxies, of the lens galaxy, using the MG formalism, the multi-Gaussian expansion formalism, which allows us to parameterize the surface brightness profile of the galaxy and use this parameterization to track the stellar mass content. But using the same formalism, we can also parameterize some dark matter halo to plug in the total mass distribution. And using this parameterization, we can simultaneously solve the lens equation describing the gravitational lensing and the Gibbs equations describing the dynamics of the system. So using this idea, we implemented a code called DieLens, which is a kind of a mixture of 3 other codes: the Dynasty, PyAutoLens, and Gem. And with DieLens, we are able to model this. We are able to perform the self-consistent modeling, very straightforward. But we can also model only the dynamics and only the lensing observables using this multi-Gaussian expansion framework. And to test this framework and see the advantages and bias, we create a sample of mock observations based on the Illustris TNG 15 hydrodynamical simulations. And this sample tried to reproduce AST and Muse-like observations. So in the end, we have 21 mock observations that we will model, use DieLens, and we will compare the results of this combined modeling with results obtained using only the dynamics and using only the lensing information. And just one thing that is important here, we are calling this dataset the fiducial dataset because we have 35 binks in the kinematical map. And this is important because at the end of the presentation, I will show how the change of this number of constraints change the outcomes of the combined modeling. And to model this mock sample, we apply a pipeline that breaks this modeling in the 5 stages, beginning from using a parametric source and gradually increase the complexity to finally use a pixelized source model. And we describe the total mass distribution using a stellar component and a dark matter, a generalized NFW profile to represent the dark matter halo. And so just talking about some of the results here, I'm showing the fractional difference in 3D enclosed quantities within 2.5 effective radii for the dynamical model in black and for the self-consistent modeling in blue. And each panel here show different quantities. This first one, the top left, is the stellar mass, then the dark matter mass, the dark matter fraction, and the total mass. And the insets shows the median and the spread, 1 sigma spread around the median value. And what we can conclude from this plot is that we can accurately recover the stellar mass and the total mass with a fractional error below 10%. And in particular, for the total mass, we have a good spread. I mean, the spread is relatively low around the median. But the bad news is that from the dark matter quantities, like the dark matter mass and the dark matter fraction, the error is quite large in the median value and also have a large spread, which is very bad if you are modeling only a few systems. This plot follows the same idea as the before. So we are seeing the fractional differences, but in this case, this is for 2D enclosed quantities within the Einstein radii. And now in red, we are seeing the results coming from the lens-only modeling. And again, we have similar results in the sense that the stellar mass is well recovered, as well as the total mass with relatively low spreads. But the dark matter quantities, it's bad again. I mean, even in this case, for the dark matter fraction, where we have a low median fractional error, this spread is quite large. So we are always covering the entire interval, which may suggest that if you are interested in a population level, this is fair to apply. But if you are trying to infer properties of one single galaxy, it's really difficult to make any great affirmation about the system because of the spread is really large. And this poor recovery in the enclosed quantities is reflected in the parameter estimation of the dark matter halo. So here I'm showing the parameters of the dark matter. So this is the outcome, I mean the result of the model as a function of the input in the model. For the three models, in orange is the dynamical model, red is the lens model, in blue is the combined model. And we are seeing in the upper panel the scale radii of the dark matter halo, and here in the lower panel, the inner slope of the dark matter halo. And what we are seeing is that we are not constraining any of the parameters very well. And we also have a large scatter. So this is the kind of thing that we are seeing reflected in this kind of plot. Since we are not able to constrain the parameters very well, you are not able to recover enclosed quantities very well. And as I said before, this is my last plot. We want to see how the number of kinematical constraints or the number of kinematical beams impact the outcomes. So we run the modeling again, but varying the number of kinematical constraints in our kinematical data. And here you are seeing the results for in black using 35 beams in the kinematical data, in blue using only 15 beams, and in red using 55 beams. And what for 3D enclosed quantities. And again, all these plots shows the fractional difference. And what we are seeing is that the number of kinematical beams doesn't seem to impact the outcomes, at least not in this range of variation that we test. And this is something surprised, but because one of our initial thoughts is that if we increase the number of kinematical constraints, we will be constraining the data and the mass profile more accurately. So this should improve the outcomes, but this is not what we saw in the results. So just to my take-home messages, but to say before that, we have other results and other plots regarding the density slope, other quantities within the Einstein radii. We also have results regarding the change of the dark matter assumption. So if you want to know more about this or discuss other things, you can come talk to me, and I'll be really happy to talk about this. But the take-home messages is that we can do a pretty good job in recovering the total mass profile and recovering the total density slope, which is interesting for many gravity probes. Recovering the stellar mass distribution of stellar mass can be a good thing, but this is model dependent, so it depends how your assumptions. All models are really bad in recovering dark matter parameters, so this is really sad, actually. And the model seems to be insensible to the number of kinematical constraints, which is something interesting to keep in mind when doing proposals for like IFU observations, for instance. So what's now? We want to apply this to real data to see what we got. And also we want to improve the methodologies in the sense like, are these mock galaxies fair, or is possible to improve the constraints of the dark matter parameters? If so, how can we do that? And also we want to investigate the impacts and the biases in the sleep parameter, because the sleep parameter will be somehow degenerate with all the other parameters in the lens model. So that's all, and thank you for your time.
Thank you, Carlos. Great talk. So do we have any questions for Carlos? Martin has one. Yes, so I have a question regarding your last conclusion about the insensitivity to the number of kinematical constraints. So you ran three possibilities, right? Yeah, 15, 35, and 55 bins. So what if you have like 3 bins or 0 bin, one coarse grained measured of velocity dispersion? How does this scale down to 1?
Yeah, that's an interesting question. I mean, we didn't test this because here we are trying to reproduce some Bose observations, and we expect to have at least like 10 or 15 beams because we need some special resolution to run the genes anisotropic modeling. So yeah, that's the thing. But I would say that with only one measurement, we are not able to run a full genes anisotropic modeling. So at least I didn't expect to reach the same results with just one beam. But this is just a guess.
Hello, hi Carlos. So thanks for the talks, David here talking.
I
So,
believe.
uh, well, besides this question of Martina, also you said that it was hard to recover the dark matter parameters. You had
Yeah.
but my question is, so it was not clear to me how bad it was, and if you, but in our case, you're considering data from lensing as well, both the cinematics and the lensing.
Yeah.
So, and what was the improvement of the lensing? So, how, with the lens, was the improvement on finding the dark matter parameters, right?
Yeah. In the spot, I don't know if you can see the insets here because maybe it's too small. But using only the dynamics, we have a median fractional error of 27%. If you are modeling only the lens, this goes to 12%. And if you are doing a combined modeling, this goes to 1%. Okay, in the median value, we are getting better. The problem is that the spread in all the three modelings are really worse. Like we are covering the entire interval and even more than that. This is for the scale radii. But it's very similar to what we see in the inner dark matter slope.
Yeah.
So
I'm a bit
yeah,
confused. Why with lens alone, it seems that we're getting a better precision. It is because you say that dynamically you say that it's 27%, it's good 27 dots and 27%. Then for lensing
yeah,
12%. I was because with lensing we are considering only strong lensing, so it's
yeah.
you only sensitive to the mass that's inside the Einstein radius. So I was not expecting for you to be more sensitive to dark matter parameters with lensing alone. Is
With
this?
lens and yeah, actually, we still don't know why exactly we are getting these better results, but with lensing only.
Yeah.
But the Einstein radius, uh, it's almost as the same size of the kinematics. Actually, it's a little smaller. So maybe we are constraining in some way better the inner. This is I'm just I guess here. I'm not sure about this, but maybe you are constraining the inner slope well with the lensing data, and this is reflecting also in the scale radii. But in the end, I'm not sure about any of this because the data doesn't cover the scale radii. So we are not constraining this for sure. So I don't know if this is only some kind of degeneracy in the modeling, and the sampling, maybe it's better for the lensing or not. I'm not sure. Or it relies on the assumptions about the axisymmetric genes modeling and the assumptions regarding the lensing.
Curious. Okay. Okay. Well, thanks. I would like to see further details afterwards. Okay. Thanks.
Okay, nice.
Okay, so we don't have much time to questions, so let's thank Carlos again. And now we have a talk from Felipe. So okay, so now we have a talk from Felipe. So Felipe, when are you ready? I think it's good.
Começa tudo, não? Tá. Ok, vocês podem me ouvir? Tá, acho que agora sim. Tá, então, a relatividade geral é uma descrição geométrica da gravidade, ela foi publicada em 1915. Ela passou por vários testes desde que foi publicada, sendo que o primeiro grande teste dela foi em 1919, durante um eclipse solar, que foi acompanhado em duas localidades do mundo, sendo uma no Brasil. Depois disso, foram feitos vários outros testes com maior precisão, ainda dentro do sistema solar, usando sondas e a espaçonave Cassini. Saindo um pouquinho do sistema solar, também foram feitos outros testes, como impulsares. Mas testes em escala galáctica e cosmológica, eles ainda são um pouquinho mais raros. Eu posso citar alguns, como alguns que fizeram em galáxias elípticas, como esse que eu citei ali. Eles usaram medidas de dinâmica e de lente. Foi feito também um teste similar usando um aglomerado de galáxias. Já em escalas cosmológicas, foi feito em um redshift de 1.5, usando lenteamento de quasar e radiação cósmica de fundo. Mas por que eu estou falando de teste, mas a relatividade geral já está aí há mais de 100 anos, por que a gente tem que testar ela? O modelo cosmológico atual ele tem duas componentes, que são a matéria escura e a energia escura, que servem para explicar a falta de matéria visível e a expansão acelerada do universo. Só que mesmo que elas sirvam para explicar esses fenômenos, a gente não tem uma compreensão muito boa da natureza delas. Além disso, também tem a chamada tensão de Hubble, que é meio que uma discrepância entre diferentes medidas da taxa de expansão do universo, usando observáveis do início do universo e do universo atual. Como uma contrapartida a isso, foram propostas algumas teorias de gravidade modificada, mas não se tem ainda uma ideia clara de que o problema seria a relatividade geral ou todas essas coisas que eu falei. Então, tipo, a relatividade geral ainda continua dominando. Por isso que a gente precisa testar ela sempre, para provar que o problema não é ela. O problema são talvez as outras coisas, que a gente não tem uma compreensão tão clara. Ok, já que eu falei de testar a relatividade em escalas galácticas, uma forma de testar é com o parâmetro de deslizamento gravitacional, que a gente representa com a letra eta. Ele é uma razão entre dois potenciais, que é o potencial newtoniano, que ele é sensível a movimentos não relativísticos, e o potencial de curvatura, que ele é referente a movimentos relativísticos e a métrica do espaço-tempo. Quando a gente assume relatividade geral, esse parâmetro eta ele tem que ser 1. Isso significa que os dois potenciais eles devem ser iguais. Se tiver qualquer desvio em relação a esse parâmetro eta, então tem algum problema com a relatividade geral, o modelo que a gente está usando. Por causa da natureza desse parâmetro de deslizamento gravitacional, a gente pode traçar os potenciais de maneiras diferentes. Usando a galáxia, que é a lente, no caso, a gente pode usar a cinemática do gases das estrelas para poder traçar esse potencial. E, por consequência, calcular a massa dinâmica. Mas também usando o efeito de lenteamento gravitacional, a gente pode traçar os dois potenciais e medir a massa por esse efeito de lente. E com aquela equação ali, tem o... Ah, tá aqui. Aqui, ó. Com essa equação aqui, a gente pode comparar essas duas massas e, assumindo a relatividade geral, as massas têm que ser iguais e o parâmetro eta vai ser igual a 1. Então, até agora foram feitos esse tipo de teste em escala galáctica usando galáxias elípticas, como esses dois que eu citei aqui. E os resultados eles estão em acordo com a relatividade geral, dentro das incertezas sistemáticas e estatísticas. Mas tem uma predominância da sistemática nesses casos aqui. E uma coisa que a gente pode fazer é combinar os traçadores dinâmicos para poder quebrar essas degenerescências associadas à modelagem dinâmica. E uma maneira de melhorar esse método é usando galáxias espirais, que elas têm mais um traçador dinâmico, que seria o gás. Então, as galáxias espirais são o tipo que eu vou abordar a partir de agora. Elas têm um bojo central, ao redor delas tem um disco rotacionando, tem uma estrutura de braços em espiral e um halo galáctico. Elas também têm barras que se deve ao fato das estrelas mais no centro desviarem um pouco da sua rota, e elas podem ter essas barras elas podem ter um papel importante na evolução dinâmica. Esse tipo de galáxia, o movimento que prevalece nela é de rotação, tanto de estrelas como gás. Mas ainda tem um pouquinho de dispersão de velocidade das estrelas. Aqui nessa figura dá para ver que na parte mais central ela é mais avermelhada. Isso é porque, em comparação ao disco, a parte mais central tem estrelas de população mais antigas, e a parte mais do disco, a parte mais externa, tem populações mais novas e regiões de H2. Só que tem esse tipo de galáxia tem um motivo para que ela não tenha sido tão abordada até agora com um efeito de lente. As galáxias espirais de todas as lentes gravitacionais, elas correspondem a aproximadamente 10 a 20% de todas as lentes. Essa fração ela vai poder ser confirmada depois com a classificação de Last Biro do Renan, do pessoal do CBPF. Então, até então, a gente tem uma maioria de galáxias elípticas como lentes gravitacionais. Isso pode ser explicado pelo fato de que, mesmo que as galáxias espirais elas sejam bem comuns no universo, é muito mais provável de encontrar uma elíptica que seja massiva do que uma espiral que seja massiva. E no efeito de lente, é a massa da galáxia que vai definir a área ao redor da lente que a galáxia fonte que está no fundo, ela precisa estar para poder ser lenteada. Então, quanto mais massiva, melhor o efeito de lente. Tá. Como eu falei da rotação nessas galáxias, a gente tem uma ferramenta importante para poder para poder estudar a distribuição de massa, que são as curvas de rotação. Nas galáxias espirais, a gente tem um movimento ordenado de gases e estrelas e ele acontece ao redor do centro. Aqui nessa figura, que foi retirada de um trabalho da Vera Rubin e seus colaboradores, a gente tem aqui no eixo horizontal a distância até o centro da galáxia e no eixo vertical a gente tem a velocidade rotacional. Aqui tem várias curvas de rotação diferentes, de diferentes tipos de galáxias. Só que todas elas têm algumas coisas em comum. Elas têm um rápido aumento da velocidade e depois ele tem um achatamento na curva. Dá uma estabilizada. Isso pode ser explicado pela presença de matéria escura, já que a tendência seria a curva dar uma decrescida por aqui por ter uma menor quantidade de massa. Ok. Falando agora sobre os objetivos do meu trabalho, do meu projeto, a gente vai testar a relatividade geral em escalas galácticas usando uma galáxia espiral que atua como lente gravitacional, que eu já falei. A gente vai modelar as massas dinâmicas de lenteamento ao mesmo tempo, usando o DyeLens, que é um código que eu já vou falar um pouco mais para frente, e usando também os modelos de lente de melhor ajuste para poder reconstituir a imagem da fonte. E com isso vai ser possível derivar algumas propriedades das lentes espirais, como massa estelar, massa de matéria escura, fração de matéria escura e razão-massa-luz. Também vai ser possível inferir aquele parâmetro de deslizamento gravitacional que eu falei lá no início. E até onde a gente sabe, esse vai ser o primeiro teste da relatividade geral em escala galáctica usando espirais. Em relação ao sistema que a gente foi escolhido, a gente escolheu um sistema que já estava disponível na literatura, com dados de fotometria e de cinemática, porque o tempo do mestrado é limitado. Então, eu não teria tempo de pedir tempo de observação, fazer redução de dados. Então, a gente escolheu esse sistema aqui, que ele já foi estudado, ele está um redshift de 0.14, a fonte dele está um redshift de 0.71. Ele foi originalmente descoberto pelo survey do SLACS e depois foi incluído no survey do Swells. Ele já foi estudado em outro projeto, só que com o propósito de medir a contribuição relativa de matéria bariônica e matéria escura. Para esse objeto, a gente tem dados de fotometria de alta resolução no óptico e no infravermelho próximo, com o Hubble e o Keck. O Hubble no óptico e o Keck no infravermelho próximo. Aqui no lado a gente tem essas figuras, essas imagens. Essas três aqui são do Hubble de diferentes filtros, e essa aqui, no canto inferior direito, é do Keck, que é no infravermelho próximo. E essa imagem aqui ela é um pouquinho menos sensível à poeira, então dá para ver melhor o arco sendo lenteado aqui à esquerda do bojo. A gente também tem dados de espectroscopia, usando o espectrógrafo Demos do Keck. É um espectro em fenda longa, no óptico. Aqui, essa aqui é a imagem total do espectro. No eixo horizontal, a gente tem os comprimentos de onda observados. E no eixo vertical, a gente tem a distância em relação ao centro. Tá, aqui essas são algumas das linhas de emissão. No caso, eu vou usar a de H-alfa, porque ela fornece medidas mais precisas de velocidade. Sobre os métodos, a gente vai subtrair a luz da galáxia ao redor do arco, fazendo uma reflexão da imagem e subtraindo ela mesma, para poder sobrar só o arco. Aqui não está muito nítida, eu tenho que melhorar essa imagem ainda. Não é definitiva. Esse arco ele vai ser isolado da imagem subtraída e vai ser feita a reconstituição da imagem fonte, usando o método de inversão linear com o código do PyAutoLens, que ele consegue reconstituir a imagem da fonte assumindo o modelo de massa para a galáxia lente. Aqui a gente tem um exemplo do modelamento. É isolada os arcos do efeito de lente e depois é reconstituída para ter uma imagem da fonte, para ter uma ideia de como que ela é originalmente. A gente pode analisar também com isso a estrutura de massa da própria lente. Além disso, também vai ser obtido curva de rotação do gás ionizado e o perfil de dispersão de velocidade das estrelas. Com esses dados também depois disso vai ser modelada a curva de rotação e perfil de dispersão de velocidades usando o GEM. E com isso vai ser comparado essas medidas reais com as medidas do modelo, para poder testar o modelo de massa e ver se ele está de acordo. A etapa do trabalho, essa aqui é a curva de rotação que eu fiz, eu extraí daquele espectro. Foi feita usando a linha de H-alfa. Eu usei uma tarefa do IRAF chamada RV Lines para poder ajustar gaussianas aos picos de emissão e medir a diferença entre esses picos tipo, quanto mais longe do centro, eu medi a distância desses picos até o pico do comprimento de onda de repouso para poder medir a velocidade. E com isso eu consegui montar a curva de rotação. Além disso, também vai ser feita a modelagem da dinâmica e da lente ao mesmo tempo, assumindo um perfil único e autoconsistente de massa para os dois casos. Para isso, o componente de massa estelar ele precisa concordar com a luminosidade observada da galáxia lente. E também a gente vai assumir uma razão massa-luz constante por toda a galáxia. Para matéria escura, a gente vai usar um perfil NFW generalizado. Aquele código que eu falei, que é o da Lens, ele foi desenvolvido pelo Carlos, que acabou de apresentar o trabalho. Ele consegue incluir a modelagem, ele consegue fazer as duas modelagens ao mesmo tempo, de lente e dinâmica. Nesse caso, como eu estou trabalhando com galáxia espiral, eu vou ter que incluir eu vou ter que incluir uma parte para calcular, para modelar a curva de rotação. Eu digo incluir porque esse código ele foi desenvolvido para galáxias espirais, elípticas. Então eu vou ter que fazer uma adaptação para poder usar nesse meu projeto. E era isso.
Ok, Felipe, obrigado. Então, a gente vai para as perguntas agora. Alguém tem alguma pergunta? Imagina. So that's a very nice project. If you wish, I will ask them a question in Portuguese.
No, no problem.
No, okay. A question is, maybe it's a tricky question, but like a very important step in your work is to generalize the dye lens to include this rotation curve. Do you have in mind what to do already to make this generalization, how to include the rotation curves combined with the velocity dispersion in the dynamical modeling? Is this something like well known in the, I'm ignorant about galaxies. So in the side of modeling the dynamics of galaxy, is this like already available without the lensing, modeling the rotation curve plus velocity dispersion? Is this something already available and you have to adapt to dye lens to include the lensing, or?
Well, we will use GEM to model the rotation curve. So I will try to include in dye lens, make some adaptations to see if it works.
So this GEM software already includes rotation curves.
Yeah.
Thanks.
By the way, about the rotation curves, I think it will be easy to implement because the equation. The equation is easier than the case of genes. For genes, the equation you need it for when you have dispersion, but when you have some object that's supported by rotation, it's simpler. So I think it should not be an issue. I think. But anyway, another question that actually could do this question also to Carlos. But I see that you both are work with the generalized NFW profile. I don't know if you know, but this is a very phenomenological dark matter halo. You don't derive it. It's just a phenomenological extension of the NFW profile. Why, for instance, don't you use either the NFW, the pure NFW, as a first test, or the ANAST profile? But the ANAST profile indeed comes from simulations and generalized NFW, and it was shown to be a better model to match the simulation than NFW. Have you thought about that or no? No, okay.
No.
Okay, so just a suggestion. Just
Okay.
I would say I in my position, I would, while we were developing this, first test with the FW because it's easier. It's good to start with simple models, and once it's okay, I would either stop at that point or proceed to a nice two. I'm not so interested on GNFW, but okay. That's okay. That's observation. And just one more issue that was not clear to me about the radius of the Einstein ring. Is it goes far beyond the bulge of the galaxy? I could not get that.
Could you repeat?
Yeah. You're considering Einstein ring, right? The length of this Einstein ring radius goes far beyond the bulge of the galaxy, or is it inside the bulge?
Não,
Você pode falar em português, né?
Tá.
Melhor. Tá.
Ele tá sendo lenteado aqui do lado. Ele tá sobrepondo o disco, mas ele não tá sobrepondo o bojo. Não sei se é isso que tu perguntou.
Você está indo, então, ele vai além do bojo.
Sim.
Mas ele vai muito além do bojo? Ou tem qual? Meu questão é o seguinte: se o Einstein Ring ficar muito no centro, essencialmente o que você está modelando é o bojo com lentes, né? Para a lente ser relevante para você modelar com rotação, você precisa que o anel de Einstein, né, vá um tanto longe do bojo, né? Só que não ficou claro pelo desenho, assim, até onde está indo, até onde essa galáxia, você tem dado dessa galáxia até que raio, até onde está o bojo, mas
Eu não me apeguei a essa parte. Não. Mas eu comparei com outras imagens também de outras galáxias e acontece uma coisa parecida, assim.
Tá.
É mais ou menos para essa região.
Não, bem, de qualquer jeito, eu acho a proposta muito interessante, que eu acho realmente bom. Você aí não tem problemas com equação de Jeans, que tem outras complicações. Então, eu acho a proposta muito boa e depois a gente pode conversar mais com o caso. Obrigado.
Okay, so I think we have more time for one question, or also a question for Carlos. I mean, we are already on the discussion on talks section, so I think we can make a question for Carlos as well. So, any question? Do you have any question from the online?
So can I have a comment about what David was saying about the GNFW profile and the INASTO?
Yeah, sure.
Maybe I should turn on my camera. So yeah, in my case, at least, I'm using the GNFW profile because we are deriving our mock data from the Illustris TNG, and this the subhalos in the TNG, I mean, the particle data that we extract from the cosmological simulation have some core in the central regions that can, it's debated if this core is true or a simulation problem, but there's a core there. So we try, I try 3 different profiles, 3 or 4, I can remember, but I try the GNFW profile, a simple NFW profile, a INASTO profile, and one core profile. to see which of these profiles fits better the subhalo dark matter distribution. This before applying the combined modeling, because I was trying to see which one of these profiles is better, represents better the distribution. And in my case, the GNFW profile was the profile that fits better. So I'm using this one just because the simulation, in some sense, are better reproduced by the GNFW profile. But I agree that the GNFW profile is not the best one. But since we have this issue with the simulation, I'm trying to like fit what the simulation have to see what we got. So this is why I'm using the GNFW profile and not a NASTO or some chord profile.
Okay,
I don't know
yeah.
if this answer your question, but this is my motivation to use a GNFW and not a simple NFW profile, for instance.
Yeah, so okay, thanks for clarifying. But anyway, not that there is a problem in you studying the GNFW, it's just because it's harder than the standard one, and
Yeah.
yeah, in my case, I would not care that much with GNFW and go to NASTO, but okay, I understand your point as well. Perhaps okay, you're using a phenological one because in your case, you'll find a better reproduction with the type of simulation that you are doing. Yeah.
Yes. Yes.
So, yeah, that's okay. No, so thanks.
Can I also make a comment on that?
Yeah, sure.
Yeah, but thanks, David, for the suggestion. Yeah, in principle, we can implement any dark matter profile in Dylan, so definitely we can test it. And for Felipe's project, this was the one that we tried first, but for sure for the final result to also to investigate systematics, we have to vary the profile assumed for the dark matter. So maybe that's another one that we can test.
Well, in case you like also test other profiles, there's this into 14 that's also it's interesting to, but okay, this A-nice and the C214 they are more troublesome and they are harder to deal with, but perhaps it's in case you are interested in other ones, but just because for the GNFW profile you have to deal with the three independent parameters. This, or you consider some correlation among them?
No, I think for the GNFW, no, it's there.
At the GNFW, you should, I mean, a priori they depend on the virial mass, the virial radius, and gamma, the slope. Just first to check that, are you using the three parameters uncorrelated, or are you putting some correlation among these parameters?
Uncorrelated so far, Carlos, right?
Yeah, so far we are letting all the parameters free, but we, as I said, we have other assumptions. And one of our assumptions was fixing the scale radii into 10 times the effective radii of the galaxy. This is a common assumption in the literature. So with that, we reduce the number of profiles to see if we can constrain the other two parameters that we left free better. And yeah, we got some better results regarding the enclosed quantities when you fixed the scale radii, but still with a large spread. So we can reduce the median fractional error, but the spread and the recovery of the other parameters still not as good as we wish.
Thanks. Well, anyway, we may discuss afterwards. It's also a pleasure to
Yeah.
discuss.
Thank you.
Yeah, all right. I think we are a little bit ahead of the time, so I think we can thank again Felipe for the talk. And now we go for the coffee break section. Okay.
Morning. Morning. So now we're back from the break. I assume people from Zoom, we don't see them here usually then, the little windows. Ah, okay. So I have the most important person for the moment is Graciele, obviously. So our next talk will be from Graciele Becerra. She'll be talking about the impact of galaxy dynamics and modified gravity constraints. Sorry, impact of galaxy dynamics on modified gravity constraints from Einstein rings. You have 15 minutes, Graciela.
Ooh. Okay. Wait. Okay, you all can see my screen?
So we can see it.
Okay, perfect. Just let me put in full screen mode. Oh yeah, present here. Okay, so good morning, everyone. I am Graciele. I was a master's student at CPPF. I was supervised by Professor Martini, co-supervised by Professor Cristina, and I finished my master's on July last year. And I will show you a little bit of what we find with the study that we did in the 2 years of my master's. So just very brief, the background of our study. We can test gravity and we can test general relativity with a strong line system. If we write the metric of space-time, we can write it in function of a Newtonian potential and a curvature potential. And then we have what we call the post-Newtonian parameter as a ratio of these two potentials. So if you have a strong line system where our lens is a early type galaxy, the cinematic of the stars in this lens will depend only on the Newtonian potential. On the other hand, the lensing effect depends on a combination of both potentials. So we can combine these two observables to impose constraints in gamma ppn. Okay, so my work focused especially in the dynamics of the lens. So if you are modeling the dynamics of this lens, we have to solve what we call the Jeans equations, and we solve for the sigma O. They are the radial components of the velocity dispersions of the stars in this galaxy. So to solve the Jeans equations, we need to define what we call a brightness profile that we consider to be a power law with adjustable slope. We also need to define the mass profile of this lens, and we do that by defining a mass density profile that we are also considering to be a power law with adjustable slopes. And beside that, we also need to define what would be our anisotropy parameter, that is our parameter beta. And this parameter measure how the tangential component of this velocity dispersion differs from the radial components. What's challenging about these parameters is that it cannot be measured direct to observations. But in all kind of sorts of measurements we have about beta are indirectly inferred either to observation or to N-body simulation. It's very common for people in the literature that do this kind of study of constraining gamma using strong lensing to consider beta to be constant. So we found several papers where they did that and they consider beta to be constant. But any assumptions that we make about beta can be sorts of systematical error in our measurement of gamma. So in fact, if you consider beta to be constant, your equations are much easier to solve. You can solve them, and all the equations you can solve analytically. So that's probably why most people do consider it to be constant. But if you look to the literature of galaxy dynamics, specific for ETGs, normally what people will suggest is that beta is not constant, but it varies with the radius of the galaxy. And we have a very generic parameterization of beta, where we have a value for the center of galaxy, for when the radius goes to 0, and a asymptotic value of beta. And we also have a transitioning radius, where we can go from one value to another, that for this work we consider to be a parameter, adjustable parameter A, times the radius 200 of the galaxy. What is the radius 200 of the galaxy? Is the radius where the average density of the galaxy is equal to 200 times the critical density of the universe. And that's what we will consider to be our transitioning radius in the beta model. So what we did, we chose 3 models from the literature. So this Ozikov-Mehi model, that is a model from the 80s, but until today it's very useful across several studies to model the dynamics of ETGs. We also consider the model of Mamon and Lucas from this paper from 2005. And also we consider this model called generalized He, that is kind of a generalization of the Mamon and Lucas model, but we fix beta 1 in half, so we can compare to Mamon and Lucas, but we let beta 0 to be free, so we can like test the limits of this model. Okay, so we was able to calculate sigma R for all those models, but sigma R is not a quantity that we can compare to observational data because it's just a radial component. So for us to be able to compare to the observation, what we do is calculate what we call the velocity dispersion of the line of sight, or the sigma loss. So we basically project the sigma R in the plane of the sky, and we integrate toward the line of sight. And once we have calculated the sigma loss, we can calculate a weighted mean of the sigma loss, and we weighted by the brightness profile of the galaxy, and a weighting function that will take in consider the observational conditions, such as the size of the fiber that would take the spectra of this object and the atmospheric scene of this observation. So by doing this, we obtain a theoretical model that we can compare directly to the velocity dispersion, the measured velocity dispersion. So with this theoretical model, we compare this to the measurements by defining a likelihood. And this likelihood, we can use this to define a posterior that we will maximize so we can get a measurement for the model parameters. This posterior is calculated using the likelihood, and we also consider priors for each parameter, that this prior will insert or not a bias towards something that we already know about these parameters. So, for example, for the slope of the density profile, we consider a prior a Gaussian centering in 2, because a ETG can be modeled to be a singular isothermal sphere, and that's normally the value we consider for this kind of system. To the slope of the brightness profile, we use a Gaussian prior centering 2.4. This is the measurement come from this paper of 2010. For the gamma PPN, because this is our parameter of interest, we didn't want to insert any bias in our measurement, so we consider the prior to be flat, and we impose a limit between 0 and 10, but more for computational reasons, so we can make a faster. So for beta, we consider beta constant with different priors. We test different priors for beta constant. And we also made one run with a flat priors by letting beta run freely without any bias. For the cases where we have a radial model, the radial model has its own parameters, A from the transitional radius and beta 0 from the case of generalized T. For this case, we let flat priors for these parameters because we didn't find any strong justification in the literature that would justify any priors, any bias in these parameters. And we use a technique of MCMC to explore the space of parameters. We applied this methodology to a data set of 8 systems that was compiled by Cao et al. In this paper of 2015. All these systems had measurement from the slow one for the sigma, for the velocity dispersion, and a little bit of our results. So I will start with the case where we got a strong constraint in gamma ppn, in the posterior for gamma ppn. So we have the cases, the radial case of Oskov-Mehy and Mamon and Loca, and for the 3 Gaussian priors for beta constant. So we have this green curve is this priors of 0.18. This is the result from the literature, actually. This is a reproduction of the result of the literature, and this is the prior that is most used in most of the papers. This prior were calculated by this paper of 2006, where he used results from a simulation, a paper of a simulation from 2001. But we also want to consider a more actualized prior. So we also consider this of 0.23. That's from a paper from 2019, and it is calculated using antibody simulations from the Illustre TNG. And also we consider this prior of 0.45 that was calculated by Kuppen et al. In 2009. And was calculated using data of, it was observational data and was strong lens data that they used to try to estimate this value for beta. For the case where we let a flat prior on beta constant and also for generalized T that had a beta 0 that was considered to be free, we didn't obtain a strong constraint in gamma. We can see that the posterior is not well defined, it's not Gaussian, but although we didn't had a strong constraint gamma, we still observe a peak in around 1, that the expected value for gamma, especially considering that we are considering here the case of general relativity and no modification, no specific modification. So just to conclude, we have main 2 questions for this work. First, we want to test the dependency of beta in gamma. And our conclusion is, yes, we have a strong correlation of beta in gamma, and our results for gamma depend strongly on our choices of beta. And this raised some questions about possible bias in previous choice of beta, in previous works. And also, we also have a question whether we could constrain simultaneously beta or study this stellar kinematic and constrain gamma at the same time, the same experiment. And the answer is that, at least for the kind of data we was using, the kind of study we used, it's not possible to study the stellar kinematic, stellar kinematic and gamma at the same time. When every time we let some degree of freedom in beta, we end up in not strong constraint in gamma. So for us to have a further advancement in this matter, we would need a better understanding of the role that the anisotropy plays in the galaxy dynamics, and that could come, for example, from specially resolve kinematic data or more accurate cosmological simulation at subgalactic scale. Okay, so what are we intend to do now? We want to run our analysis in the sample of the last Peru. That is a more actualized sample. And also we want to publish these results. That's all.
Thank you, Graciela, for your talk. Are there any questions here on in the house, on site, or on Zoom? Well, I'll start with a question. Graciela, can you see me? I don't know if you see me. Yeah, okay.
Yes.
When you mention, I'm not as familiar with some of the things that you were discussing here, but I understand these beta measurements, the anisotropy, is part of the limitation of the number of lenses that you're studying, or because you mentioned a few tens of galaxies that you're looking at, and I wonder if this is there any data? You mentioned constraining with observations and body simulations. So I was wondering what your
It's not the number of the lens, but it's how the spectrum is take. Because what we have now, and I'm not most of my work was theoretical, was not in observation, but most of the data we have is we have that one number that is a mean velocity dispersion for each galaxy. But I know there is a possibility, and it's quite more recent, for you to not have one only value for the velocity dispersion, but you make a special resolved spectroscopy where you can have for a small pixel. That where I guess would come a better measurement of beta. So it's not, for now at least, it's not exactly the quantity of lenses we have, but the quality of data we have.
is the quality of the data or the resolution that you need to do this also spatially resolved kinematic analysis, are we talking about like Muse observations, or is this not enough? I mean, you can use this with adaptive optics. Is the state of the observations that we have now enough for you to do this kind of thing then?
Well, I
mean, to go beyond to what you have done already. I mean,
yeah. Well, the idea to run in the last Peru is just for we can publish this result with a actualizing sample. But when I say we need better understand of beta, what I'm referring to is that, oh Lord, okay, I will. We went to a conference last year that was very interesting. Let me see if I found. Well, one person that was presented a let me see if I found here. Oh God, too much slides. Yeah, he presented this where he have this kind of observation where he can make more. You have a galaxy and you have a more especially resolved calculation of the velocity dispersion. And he was discussing trying to measure beta, because here you can see that you need a variation, a radial variation of the a radial variation of beta, so it can match what you are observing. So it's another kind of data. It's not that velocity dispersion that is measured by the Sloan. That will come from new observation.
okay, thank you. Any other comments or questions? No? Okay, well, thank you very much.
Can I have one?
Sorry. Somebody spoke.
Yeah. I'm talking through Zoom. Yeah, Carlos. Just for curiosity, do you have any thoughts, Graziele, why the posterior on gamma ppm GT, I think this is gamma one of your models, has such a high upper limit. I mean, yeah, maybe you can go.
Just a minute. This one.
Yeah, that one. Yeah. Do you have any thoughts why these have sub? Yeah, the upper
you mean
limits.
you say they spread?
Yeah. Just for curiosity, because the other ones I saw has a spread, which is huge in some cases, but this one is really, really different
This
from the
one.
other
Okay.
ones.
So one thing that you should consider is that these cases here, the gamma is well constrained. So this is a Gaussian. We can calculate that. This is not Gaussian anymore. It's not very well constrained. I don't know why it can go that deep, but like it's clearly not well constrained. So like I don't know how we can trust in this bigger value. What this plot show basically is that if you have like a free beta zero, whether I will have what is just the beta zero or whether I will have a radial component, I will lose the constraint in gamma.
Yeah, interesting. Yeah, thank you.
Okay, well, thank you very much. If there are no further immediate comments, we can certainly have more questions and comments in the discussion session. So thank you, Graciele. And yeah, we can clap again. And I'll give the mic to Eduardo. Here. So our next talk is Eduardo Baladon, probing the dark energy leakage effect on kiloparsec scales through gravitational lens.
Passa aqui nesse controle? Bom dia, pessoal. Esse meu trabalho que eu vou apresentar, ele é de mestrado. Eu vou falar em português mesmo, tá? E eu venho fazendo esse trabalho com o Martins tem um ano. E basicamente a gente quer medir esse efeito de vazamento de energia escura para a escala das galáxias, escala de quiloparsec, via o lenteamento gravitacional forte. Então, desde 98, quando se comprovou observacionalmente a expansão acelerada do universo, vem se tentando entender qual é o mecanismo e quais as possibilidades que geram a chamada energia escura. Uma forma de você fazer isso é você considerar uma teoria escalar tensorial bem geral. Você considera isso em escalas cosmológicas somente, e aí em escalas menores você vai ter o que a gente chama de mecanismo de screening, de blindagem, que vai blindar esse campo de energia escura, esse campo φ. E aí você pode ter um campo φ acoplado ao escalar de Hit, como se fosse a Lagrange-Dick, ou você pode ter uma quintessência, uma quiescência, um fluido misterioso. Essa classe de teoria chamada DOST, são teorias escalares tensoriais de ordem superior, elas abarcam todas essas possibilidades, elas são bem gerais. E dentro delas está contida as famosas teorias Rondesk, por exemplo, e as chamadas Beyond Rondesk também. E aí o que você tem quando você faz teoria de perturbação cosmológica, você obtém 9 parâmetros, depende do tempo somente, adimensionais, e elas basicamente vão descrever a sua fenomenologia de energia escura. Cada parâmetro vai estar relacionado a uma característica nova dessa energia escura, se ela pode aglutinar ou não, etc. E aí, nesse trabalho, a gente vai focar nesses parâmetros alfa B, alfa T, alfa H e beta 1. Você tem esse FP, que é basicamente uma constante gravitacional que se modifica ao longo do tempo, igual acontece em Brans-Dicke, etc. O parâmetro alfa-H, ele vai ser um dos mais importantes para a gente. Ele vai dizer o quanto a sua classe de teoria está desviando de Rondesk. Basicamente, ele vai medir a mistura de termos cinéticos das perturbações de matéria com termos cinéticos do seu campo escalar. Você tem esse alfa-L, que caracteriza uma quebra da invariância de Lorentz. A gente vai estar considerando ele igual a zero. A gente tem o alfa-T, que mede um desvio da velocidade das ondas gravitacionais, o desvio em relação à velocidade da luz no vácuo. E você tem esse parâmetro beta 1, que é uma generalização para os termos de ordem maior, acima de ordem quadrática nas derivadas segundas do seu campo. E ele basicamente vai ser esse termo kinetic braiding, que vai ser um trançamento entre termos cinéticos do seu campo escalar e da métrica. E aí, para sua lagrangiana não ter problemas de estabilidade de Ostrogatsky, estabilidade de Ghost, você tem que considerar umas condições de degenerescência, são essas condições 10, e aí você só fica com os parâmetros alfa-H, beta 1, alfa-T, e você tem esse parâmetro alfa-V relacionado ao alfa-B, que é o parâmetro de Braid. E aí o que você pode fazer, você tem esses parâmetros em escala cosmológica, só que quando você considera um screening de Einstein, uma blindagem, esse campo não é totalmente blindado. Quando você tem, por exemplo, um halo de matéria escura com uma galáxia. Então, certos parâmetros vazam. E aí você tem essas formas modificadas do seu potencial, dependendo desses novos parâmetros, alfa-H, alfa-T, beta 1 e alfa-V. E aí o que você tem basicamente é o que você tem nessa imagem aqui. Nas escalas cosmológicas, você tem todos os parâmetros atuando nas perturbações, e aí, bem abaixo do raio de Einstein, você tem uma supressão da energia escura, mas aí quando você tem um halo de matéria escura com uma galáxia, esses parâmetros voltam a aparecer como se a energia escura estivesse vazando para menores escalas. E aí você consegue restringir mais os parâmetros, você pode considerar teorias mais particulares, como as Beyond Rondes, que você faz beta 1 igual a zero. Você pode considerar a observação da onda gravitacional de 2017, e aí você considera alfa-T igual a zero e alfa-V igual a menos alfa-H. E aí você tem esses parâmetros 16 que estão modificando aquele teu potencial. E aí você tem esses parâmetros livres, alfa-H e beta 1. Então, o que a gente fez foi considerar o lenteamento gravitacional junto com dinâmica de galáxias, basicamente igual foi feito no trabalho do Felipe e da Graziella, então vou passar bem rápido aqui. E aí a gente considera um perfil de matéria bariônica mais matéria escura, é um perfil polinomial, né? E aí você obtém essa equação 19, que são os seus potenciais, e aí você vê que tem esses parâmetros γ1, γ2, γ3, e dentro deles vocês têm os parâmetros de energia escura que a gente quer medir. E aí se calcula o seu desvio da lente, a equação 20. Você vai ter o raio de Einstein, que vai ser o parâmetro importante para a nossa análise. E aí agora tem a parte de dinâmica de galáxias, você vai ter uma equação de Poisson modificada, a gente considera um ρ efetivo, e aí você vai ter basicamente uma massa dinâmica modificada, dependente desses parâmetros de energia escura. E aí, por essa equação 24, a gente vai fazer como a Graziella e o Felipe já falaram, você vai querer ver, comparar essa massa dinâmica e essa massa de lenteamento. Você usa a equação de Boltzmann novamente, considera um perfil de luminosidade, esse parâmetro delta. Esse parâmetro delta, beta e alfa a gente vai considerar como os parâmetros de nuisance. Basicamente, a gente vai dar umas priors fiduciais, considerada em outros artigos, já bem usado na literatura. E aí a gente vai usar dados de dispersão de velocidade, a partir dessa relação 26, e os parâmetros de gravidade modificada entram nessa massa efetiva. E a gente considera sistemáticos observacionais também. A gente tem que integrar ao longo da linha divisada, considerar a abertura da sua slit. E aí, no final, a gente tem o nosso modelo 29, em função dos parâmetros de gravidade modificada. E agora você tem um sleep parameter, esse 30, que depende dos parâmetros alfa-H, beta 1, são os parâmetros de energia escura, e depende também de alfa, depende da sua distribuição de matéria, porque o nosso modelo, ele basicamente está quebrando o princípio da equivalência forte, então você tem como se fosse uma matéria escura, entre aspas. E uma coisa que a gente está considerando é que esses parâmetros, eles são funções do tempo. E aí você pode considerar parametrizações particulares, no nosso caso a gente está considerando que eles são constantes entre um redshift 0 a 1, que são redshift do nosso database de lentes. A gente também normaliza os dados novamente, para não adicionar para não ter um bias a mais por causa da sua slit e o tamanho das galáxias no céu. E os dados que nós utilizamos foi do Leste Beru, compilados pelo Renan. São, por enquanto, pelo que se sabe, são o maior número de dados que se tem na literatura, são 280 sistemas galáxia a galáxia, early type, e preparados para fazer esse tipo de análise de constraint de sleep parameter. Então, esse foi o nosso primeiro resultado. A gente considerou Gaussian priors, fiducial priors para esses parâmetros de nuisance. A gente considerou uma flat prior em alpha H, sem limitação, mas a gente teve que considerar uma limitação no beta 1, e a gente colocou entre menos 10 a 10. Como não tem nenhuma restrição na literatura em cima desse parâmetro, a gente admitiu que esse parâmetro, como ele aparece a nível perturbativo, ele não pode ser muito maior do que uma ordem de grandeza. E o que a gente obteve foi uma gaussiana para esse parâmetro alpha H, e o beta 1 ele não foi restringido, a gente obteve uma flat prior. E isso acontece porque, como a nossa Gaussian prior em alfa, do seu perfil de matéria, é isotérmico, por causa da conspiração Bush-Halo, né? De perfil isotérmico, você acaba que todos os parâmetros de gravidade modificada no seu SLIP, que dependem desse parâmetro beta 1, eles acabam sumindo. Então, seu parâmetro beta 1 na escala de galáxias, ele fica unconstrained. Ele só vai ser melhor restringido em escalas de lentes mais massivas, como de clusters. E aí, o resultado final que a gente obteve para esse alfa H foi 0,037, com um desvio de um sigma de 0,032, que até então, para esse parâmetro, é o mais preciso nessa escala de galáxias. A gente também consegue restringir beta 1 igual a zero, e aí a gente vai estar restringindo teorias beyond Rondeski, e a gente obtém essa gaussiana, com o valor da mediana bem parecido, 0,035, só que o valor do seu desvio agora vai ser 0,025, vai ser mais restritivo no seu valor, na sua estimativa. A gente compara esse último valor com valores obtidos na literatura. São poucos valores obtidos na literatura. Na verdade, normalmente a literatura restringe somente o parâmetro gama 1, gama 2 e não diretamente alfa H, então a gente teve que propagar o erro. E a gente tem valores na escala de clusters, esse em violeta, e a gente tem na escala do sistema solar, esse em verde, e a gente consegue ver que o nosso resultado é bem preciso, em comparação com os resultados de cluster, por exemplo. A referência que a gente está utilizando também tem uma segunda solução. Quando você tem o screening de Vasta, você consegue basicamente colar soluções, você tem mais de uma possibilidade de colar soluções nesse caso. Então, você tem uma segunda solução. Com essa segunda solução, o seu SLIP é como se fosse um gama ppn. Ele não vai depender da sua distribuição de matéria. E se você considerar que a velocidade das ondas gravitacionais é igual à da luz, você fixa αt igual a zero, e aí você vai ter que seu SLIP é 1 mais αh. E novamente considerando αh constante. A gente novamente obteve um resultado muito parecido com o anterior, de mediana de 0,036 e desvio de 0,025, e é um valor muito parecido com o anterior porque meio que é uma conspiração. Como o seu perfil é aproximadamente isotérmico, as duas soluções são bem próximas. A gente comparou esse resultado também com resultados da literatura. Esses outros resultados, na verdade, são resultados de gama ppn, mas como o nosso SLIP ele é constante, a gente considera como se fosse um gama ppn, e daí a gente tem esses resultados. A gente tem em verde resultados históricos de gama ppn, de SLIP, da literatura, a gente tem da Voyager, a gente tem de Eclipse, de 2017, e esses em azul são também medidas de strong lensing, e os que têm losango são medidas particulares feitas somente com uma lente, uma galáxia. Tem uma até que foi feita pelo Carlos aqui. E aí todas são compatíveis entre si. A nossa medida, em comparação com a de lente, até agora é a mais precisa da literatura, com relação a esse parâmetro, e é compatível com a relatividade geral em 2 sigma. Em 1 sigma não, mas em 2 sigma é. Então, basicamente, foi isso que a gente fez. A gente também comparou com outros modelos cosmológicos de background. A gente considerou um flat lambda CDM, do Planck 2018, mas a gente considerou novos outros modelos de background, como o WCDM, energia escura variável, só que tem pouco efeito na sua modelagem de lente. E aí, novamente, como eu já tinha mencionado, o parâmetro beta 1 ele não pode ser muito bem restringido na escala de galáxias, você tem que restringir ele em escalas maiores de clusters. E para um trabalho futuro, a gente quer considerar outras parametrizações dessas funções, não necessariamente ser constante esses parâmetros. A gente quer também medir alpha-H via time delay por dados do Holy Call. E basicamente foi isso o nosso trabalho. Queria agradecer ao Martim, todo o grupo de lentes da CBPF, senão esse trabalho seria impossível de acontecer. É isso, obrigado.
Comentários?
Tive uma dúvida, eu não entendi quando você colocou os priors. Obrigado pela apresentação também, eu esqueci de dizer. Mas quando você colocou os priors, eu não, acho que você falou de alfa, beta e delta. Eu esqueci qual é a definição desse alfa, beta e delta.
Então, o alfa está associado ao slope do seu perfil de matéria e é
Tá.
aproximadamente isotérmico. O beta foi do trabalho da Gaziele, tem a ver com a equação de Jeans, a anisotropia. E o delta tem a ver com a luminosidade da sua galáxia, o perfil de luminosidade.
Só o delta que eu não entendi. Como assim tem a ver com perfil de luminosidade? Não entendi. O que isso quer dizer?
Deixa eu mostrar aqui. Então, ele aparece na equação de Jeans, multiplicando a dispersão de velocidades. Ele é a densidade de luminosidade da sua galáxia lente. E a gente considera que a relação matéria e luminosidade é espacialmente constante para poder fazer
Ah, não, tá.
essa
Vai dar a razão
aproximação.
máxima luminosidade, é isso.
Isso.
Tá. E você colocou no prior em quanto pro delta?
Eu acho que é o mesmo da Graziele, 2,40. Vem de um artigo do Schwab.
Ah, tá. Porque tá numa banda específica, você tá colocando isso. Ok. Então,
Isso, são priors fiduciais, né? Não são os melhores possíveis, mas o Renan ele vai fazer, ele tá fazendo essa medida nos dados do Leste Beru e vai ter delta para cada sistema.
Eu tô achando só esse delta, o prior no eu acho pequeno, mas porque tá bem restritinho. Mas posso, desculpa, posso só mais uma pergunta? Ou passo por ele. Posso? Tá. Não, só no slide 25 você falou algo que eu não entendi. Phase alguma coisa. For this solution, the advanced time mechanism phase recover GR even outside the matter source. Ah, o que você quer dizer? O RV é o RV ideal, certo?
Não, esse RV é o raio de Weinstein. É o raio do seu screening.
Ah, tá. É o raio do screen.
É
Ok.
uma escala associada ao seu campo.
Mas aí eu não entendi. Que eu saiba, o screen vai Einstein funciona muito bem fora. Justamente dentro que você tem violação. Então não estou entendendo.
Não, o screening normalmente é o contrário. Pelo menos nesse caso da literatura, né? Fora você tem a cosmologia e dentro você quer resultado geral. Só que quando você considera essas teorias DOST, elas quebram esse screening. As Rondensk não quebra, mas as DOST consideram. Então você tem esse vazamento.
Não, se eu quero dentro da sua galáxia. É que você tem, que você viola o screening
Isso, dentro da
dentro da
galáxia.
galáxia. Né? Então, você diz, for this solution, the Einstein mechanism fails to recover GR even outside the mirror sources.
Ah, não, nesse caso não vai ser RG mesmo fora, porque você tem duas constantes gravitacionais efetivas que são diferentes entre si. Você nunca vai ter dois potenciais espacial e temporal da sua métrica iguais. É uma solução bem estranha. A gente analisou porque a literatura, a referência que a gente está usando utiliza, mas eles não dão explicação física além disso.
Tá, bem, ok. Um mistério, depois. Obrigado.
Um, you got like two different posteriors for alpha H.
Ok.
Did-
Here,
Yeah, in the next one, I think.
next one, ok.
Do you have two? There's two. You said there's two things that you plotted that were very similar, that were almost the same, I think.
So it's this result
Uh-huh.
and the result for the second solution, this one, because when you have an approximately isothermal profile, these two solutions are equal. I mean, this slip, eta equals 1 plus alpha H, is equal to this slip when alpha is equals 2.
So, like, what? So, is it just because they have isothermal profiles that these results are the same, or is there anything like?
Yes, it's only because of that.
Oh, okay. All right. That's it. Thanks.
Thank you.
Any questions from people in Zoom?
So I have a question. So you mentioned two conspiracies of the conspiracy, right? So if there is a thermal profile, then you both cannot measure beta, and also you cannot distinguish between the two solutions,
Between the two
right?
solutions.
So what would take you to go beyond this problem?
So one way, as I told you, is to go to the cluster scales. But you can actually constrain better the dynamics by considering independent analysis like João is doing. So probably this conspiracy is going a little bit away, I think.
Thank you.
Eduardo, obrigado pela apresentação. Não sei se eu
Thank you.
entendi muito bem, mas quando você tem um perfil isotérmico, você ainda tem um termo ali que é no sleep parameter que é proporcional à gama 2, né? Não sei por que que você não poderia ter um constraint em algum...
Então, quando o alfa é igual a 2, esse parâmetro gama 3 e gama 1 vão embora. E o beta 1, ele está dentro desse gama 1 e gama 3.
Ah, tá.
Então, esse tipo de análise é insensível ao beta 1. Mas o gama 2, quando você considera que a velocidade das ondas gravitacionais é igual à da luz, ele vira alfa H. E aí fica 3 menos 2, 1, 1 mais alfa H. Fica igual à segunda solução.
Ah, entendi. Obrigado.
Vamos agradecer então, Eduardo. Obrigado.
Thank you. Thank you.
But we actually have a discussion, a small moment now to discuss, I mean, further questions if you have for Graciele. Sorry. Graciele, ¿verdad? Yes, for Graciele or for Eduardo. Then we can pass on for a more general discussion, but any additional questions for the speakers? David. You can continue.
Please. So, just continue. I could not understand fully the issue with the Weinstein screening. Because in our case, you are not finding the screening outside the source because you're considering there's something in cosmology that does not allows you to find a recovered GR. Is this?
So yeah, I mean it's basically that. At cosmological scales, you have your normal theory, your dose theory. You have all the parameters, and when you consider the screening, there are these parameters that break the Weinstein screening.
Oh, yeah.
When it is Horndesk, it doesn't break, but there's these new parameters that break the screening.
Yeah,
It's a little
yes,
strange, but
if you can understand, because okay, so your modification said that you change dark energy. So is this your Weinstein screen said that it works as a modified dark energy?
Yes.
But sorry, your modified gravity said that it works as a modified dark energy.
yes, works as a modified dark
Okay,
energy.
That's okay. Okay, thanks.
So I'm Martin, a question to Eduardo. You have this Weinstein radius. Inside the Weinstein radius, you have the screening. So it's like general relativity. But then, so the question is, you have two typical scales, like within the second one, inner one, then you have this leaking effect. It's like dark energy GR and then dark energy again.
Yes, it's like that. It's like you have dark energy, all the dark energy properties. This modified dark energy, okay, with perturbative phenomenological considerations, and then you have the Weinstein radius, and at very small scales compared to the Weinstein radius at subhorizon scales, though, you have a suppression of this 54th. As it always happens in this kind of modified gravity theories. But then when you have a dark matter halo or any kind of matter, this screening cannot suppress those three parameters, so that you have dark energy leakage only at the presence of matter.
Right. So the question is, within this dark matter halo, then you would again have a modified gravity, like a fifth force.
Yes.
But then, like in even smaller scales, do you expect again GR, like for solar system tests and so on?
Yes, actually, in in the plots I've shown, there are measurements at solar system scales with solar physics, I think, but it's likely very compatible with general relativity. It's a very good constraint.
Right, but like in your plots, you have shown you have a very small error bars of the solar system ones, and then larger on the galaxy scale from
Yes.
your analysis. Would it be that in galaxy scales you see you are able to have a larger deviation, but in smaller scales from a dynamical mechanism you have a smaller deviation? I mean, could you allow even compatible with very small deviation in very small scales, could you still allow more significant deviation on the galaxy scale, like in few kiloparsec?
Yeah, I mean, it's very strange, but it seems to be the case since actually our result is compatible with general relativity, but as we saw, it's alpha H, it's like a little bit positive. So it means at kiloparsec scales, it means that gravity is a little bit stronger than Newtonian gravity. I mean, is that this result? But yeah, I think this is so. This is the
So I'm Karim. We should be introducing ourselves. That's true. Yeah. Taking advantage of where this conversation is going, Eduardo. For like at the end, you were talking about malleable. I think you said dark matter. I mean, other models for dark matter. Because if I'm understanding correctly, you're looking at deviations from what you would when you showed your picture, it was like that dark matter region, and then there's the dark energy suppression.
okay.
Yeah. If you consider different models for dark matter, I mean, this is what.
That's a very interesting question because these modified gravity parameters coupled to the distribution of matter. So different distributions of dark matter possibly leads to very different constraints on the modified gravity parameters.
So that's still a caveat. It's just an open caveat there.
Yeah, it's just an open caveat.
Yes, go ahead, Carlos.
So here's Carlos. I have a question for Eduardo, because regarding this discussion, when you show your results and you compare with the lens galaxy scale, we are also considering some systematics in your measurements, I mean, in the errors, or just the statistical error? Because I think that the major problems with the galaxy scale measurements in gamma ppn or that kind of stuff is related to the systematics. This is why we have so larger error bars.
Yeah. I mean, the biggest problem with this kind of analysis, without a doubt, is the dynamical systematics related to, as Graziele has shown with beta, for example. But in our analysis, we consider the simplest case. But we also consider, for example, uncertainties of the distribution of matter along the line of sight. But yeah, it's still a preliminary analysis on this kind of modified graph parameters. I mean, it's the first one of this kind, I think. So yeah, it's very preliminary. We have to take a further account of the systematics, like you did in your work with the only one system.
You know, that's really interesting, and yeah, thanks for the answer. Yeah, but it's very promising, I guess, because even the statistical error is quite small. So I think it's interesting because despite the systematics, we have great chance to have a really constrained measurement in the end. So that's really nice.
Yes, thank you. And it has a further motivation that, for example, the recent results of DES on supernovae and the results of DES on BAO indicates a tendency of varying dark energy And the way we do with modified gravity, a varying dark energy can possibly have these effects on the perturbative level that can lead to modifications at kiloparsec scales, for example.
I have a question for Graziele regarding the beta, the anisotropy. I mean, you do present several possible trends with radius, but I was wondering how you make this measure. You're able to constrain these measurements in a system by system, and I mean I guess that's the first question, and whether you have differences. I'm not as familiar with this, so I'm not entirely sure if this is something that you can constrain for individual systems, and then whether you see some dispersion in the values that you measure.
Okay, so you are asking if I constrain the radial models for each system. Okay, so in the kind of analysis that I do, no, we cannot constrain like parameters for each system individually, because what we are doing is define it's something quite similar to what a Bayesian analysis is. So you need to have several systems, and you have like a likelihood that will measurement like a likelihood to basically ask, if that is my model, what's the probability of I being measuring what I measure? And the idea is that I will have several data points, several measurements, and then I can maximize these probabilities for the parameters I have. So I cannot do this individual for each system. I do this for the whole sample. And I don't know what the other question was now.
Yeah. Hence the importance of having a large sample with the possibility of making these measurements. Okay, good.
Exactly.
Okay, thank you. Do we have any more questions or comments for the specific talks? Yeah, there's one more.
I have another question for Graciele. So like, I know you're looking at like how gamma can be dependent on the choice of model for beta. Is there any other kind of measurements that you know about things that can be like biased by the choice of model for beta?
You mean specifically for beta? I don't know if I understood your question. Sorry.
Like, yeah, specifically for the choice of the model of beta. Like, is there any other sort of physical measurements that could be biased by the choice of model of beta? Or that,
Okay,
like,
if there is other experiments that would also be biased by your choice of beta, no, I don't know, because I didn't look other measurements. I only looked to the effects of these on the measurements of gamma. But that's a very interesting question, because I know you can use a very similar methodology to constrain other cosmological parameters. And that would be very interesting to test if you have like the Hubble constant. If you could, I know there are people that try to constrain this method, the fraction of mass. That would be interesting, but I didn't look in that, so I cannot answer for sure. But yeah.
Thanks.
Sorry, can I add something to that?
Of course, go ahead.
Yeah, Carlos again. Actually, anything related to the mass measurement will be impacted by your choice in beta, because in dynamical modeling we have this degeneracy called mass anisotropy degeneracy, which is a problem that correlates the anisotropy of your dynamical model with any other mass parameter. So I think that if you have to choose a beta, this will impact the other mass measurements. So probably this will have some bias in measuring the any other mass-related quantity of the galaxy.
Okay, thank you very much. Are there any more specific questions for the talks or comments? So we now have actually what follows now. It's a broader discussion on perhaps some follow-up projects. The discussion, I mean, it ended up appearing here in the program, but it's a free discussion in whichever direction we might want to take it. David?
Okay, I have start with the comments. So now we saw some talks about either testing gravity or testing dark matter profiles using both dynamical and lensing tests together, the same galaxy. I am seeing that there's some presentation that emphasizes that you are testing modified gravity, and other saying that you are testing dark matter. I would say that's more likely from my point of view. Although I work with modified gravity, I would say it seems for me more natural to say that you are actually this kind of approach is constrained dark matter. On the other hand, okay, I'd say that it would be for me. It is more natural to think on this way because we have many things that are known from dark matter alone. On the other hand, I would say it's very nice to say if you find something that's different from if you measure the GAN-PPN parameter and find that's different from one, it's very nice to reframe this either as a test for gravity and a test for dark matter. It's interesting to see both approaches. It's not that, but I just kind of remark to say that if you find that this parameter is different from one, it's a big step to jump into modified gravity, and that's the point. Where I would say that that paper of Colette that all they talk about modified. I think it's let's say the approach is a big leap of faith to go. This is not this deviates from one, so it's not GR. Okay, just one comment. Perhaps it would be useful to start.
Yeah, I think that's a good point for discussion. I think what is interesting about this test is that in principle, we can look for a difference between the two potentials, right? Of course, there are lots of assumptions. We just heard about the assumption on beta, which I think it's an important issue. Some people have investigated assumptions on the light profile because this is the delta that appeared there. People usually do a Gaussian, they assume a power law light profile. There are some papers that they use Surgic profile. Some people assume strong prior on the power law density profile, which is alpha. Some papers don't use a constraint on alpha at all. So there are like assumptions on both the light, the mass, and then isotropy, which I think are worth worth investigating. But let's assume we are done with that. So let's assume we have shown, I don't think this is actually true, but let's assume we have shown that we understand those systematics and then we can get away with that. So let's assume that we can really measure the difference between the two potentials. This is not, I think, yet fully proven, but let's take this as an assumption. So now I think it's your point. Like, okay, you measure the profile perfectly well. So, but you still are able to measure a difference between the two potentials that could arise maybe for some dark matter model that has some anisotropy, an anisotropic pressure, for example, that would produce that, right? Yeah.
I think that because Anderson, if somehow we can measure directly both potentials and find that they are different within GR, there is a good motivation to expect them to be equal. Okay, can you hear? Yeah. But the point is that we cannot measure them directly. So it's only indirectly that we measure them by lensing, by dynamics. And when you do this kind of modeling, we do several assumptions that may not be true. So, for instance, the halo profile, one of them. Not all the anisotropic parameter is another problem. So my point that once you assume that anisotropic parameter, for instance, is constant, this may lead that the potential may seem different. Not so just because you fixed it before. My point that if there is some way to measure direct this potential, but there is not. We need the other things. We need all the hypotheses. Then indeed it will be outside of GR. But since we don't have, okay, that's.
Yeah, maybe we should divide the discussion into I don't know, in two different views. One is, yes, I call it systematics. Like if you are induced to find the difference between the potentials, maybe that's not a true difference between potentials, but just some of your modeling assumptions, like power law, density profile, power law, light profile, constant beta, etc. So that's one thing which I think I would place that in the category systematics. But let's assume for just one moment that all these systematics are understood and controlled. And then we really are sure if we find a gamma significantly different from one, that we are sure it is something real, right? Let's assume that. But even in this case, I think we cannot tell apart if it's modified gravity or actually some more exotic dark matter that is still producing a difference in the potentials because of anisotropic tensions, right? So like if neutrinos were an important part of dark matter, they would produce this kind of difference. So even in the best scenario, in the sense that we understand everything, we still wouldn't be sure, I think, if we found a gamma different from one, which is not actually the case that we are finding. So still that would be a test of dark matter in that sense, even if we understand all the rest, right? Yeah. So yeah, so I think that discussion is bringing us directly to the core of the discussion of now, which is what's next, right? Part of this discussion that we are having and all this set of talks has arisen from the very first LEGAC, from the first meeting on the lensing by Galaxies and clusters, which was held in Porto Alegre. Of course, some of us had this idea of testing gamma, testing GR. But at that time, I think we had almost no new results about that. I think Grazielli maybe was an undergrad student doing that. But basically, so we had some ideas. Let's study this. And after some years, now, some people have studied, like Grazielli, what we do if we don't assume a constant gamma. We will hear João with an end-to-end analysis. Well, I don't know if this is what he will present, but he has done an end-to-end analysis from scratch, modeling the systems, measuring velocity dispersions. That's also work from Ingrid, which we'll also present here. So this kind of analysis has been revisited in many aspects. Like beta, well, you hear from William about possible variations with density, with redshift, with velocity dispersion. So there is this end-to-end analysis. So we are trying to look into all the possible components of on this classical analysis that has been done in the literature. Well, you heard Carlos looking at a more detailed system where you have IFU data. So I think in a way we covered many of the underlying assumptions on this model, and so I think we learned something. Now the question is, what's next? Given that we had just discussed, on one hand, possible systematics that are still there. On the other hand, even if we find something, maybe what can we conclude about? It's clear that if we find gamma very significant from zero, that's very interesting, because we are finding new systematics or new physics, and that's fine. But we have not reached that point yet. So like my provocative question is, we are improving statistics, so our bars are decreasing, right? We are improving our analysis, so we are using less assumptions. But still, we are finding gamma compatible with one, which is in a way reassuring because there's no big systematics. And maybe it's reassuring because maybe we have some prejudice that GR is the right theory. So like this group is a question, provocative question. This group, are we interested in going further? And in which direction? Like just improving the number of systems and decreasing error bar, or maybe looking at new observables that may bring new information, or maybe just give up and do another interesting things. There are many other questions. That's my provocative. What are your opinions about that?
Great. Okay. So, well, ideally, it would be very nice to study, as someone present here, the case of disk galaxies, because then you have no issue on the anisotropic on G's equation, the anisotropic parameter. It's one unknown less. But on the other hand, it's not so clear to me that's possible currently because of the data, because of the radius of the lens, or how good would be this kind of constraint. But if it's perhaps with future, I don't know what it is. Perhaps with future data, it will be easier to find Einstein ring around a disk galaxy and such that the ring includes a good fraction of it. Then that would be great. But yeah. Yeah, no, I mean, yeah, yeah, the lens did this, guys, exactly, yeah, the lens did, yes, because this will be indeed it will be a clear result in the sense that there will be no dependence on the anisotropic parameter, which actually is not a parameter, it's a function. So,
right. So one of your suggestions would be like look at these galaxies. Maybe Felipe has shown a very interesting light curve, but like the arc was kind of inner. So you're saying it would be great to find like a spiral galaxy with a larger Einstein ring so that it's clearly in the disk, not that close to the bulge, so that we can do more model independent analysis. That would be one of the
yeah.
So you're pointing to new systems, not in the statistical just to increase the sample, but in qualitative difference, right?
Because another way to be to find, let's say, a universal anisotropic profile, but I don't see a way to solve this problem. I don't know. If there was, that would be great. This is the universal one. Let's use it. So the other way it would be we should not depend on that. So we go to other systems, disk galaxies.
Yeah, so that's a key thing that it's a question to the audience, maybe to Carlos that's looking at TNG. Like David said, there doesn't seem to be like a value for beta that has some, I don't know, universality. But what we see in the literature is huge, vastly different models for beta. Like those that Grazielli mentioned, they are kind of phenomenological one, this modified Tiré, all these things. And in a way, they are fitted, they are designed so that some of the equations have analytical solution. And when you look at simulation, so I think basically we don't know anything about beta, it does seem. But maybe Carlos, do you want to comment about that?
We don't know nothing about beta. Yeah, even in cosmological simulations, like we cannot have, at least as far as I know, we don't have a universal thing that will fit all the data. So yeah, but I have a comment regarding this because I'm not so used to this kind of sample analysis. So I have a question and then a comment depending on the answer on this question. Because when you model the sample data, you usually assume a prior for this beta and for the slope of the light profile and the slope of the mass profile. But you pick one value for this prior and assign this to all your galaxies, or you sample from this prior distribution one value for each galaxy and then you do your analysis? This is the first question. I don't know if I'm clear about what I'm trying to say.
Can you repeat? Sorry.
Yeah, when you have this prior on the slope, like we have a prior centered in 2, and we have all your data set, we are choosing one value and assigning this value to all your galaxies, or you are sampling from this distribution one value for each galaxy individually.
If you're using Bayesian analysis or anything like that, you are using the same prior for all the galaxies. Okay, it's
Okay,
for your
so, yeah.
whole, if your whole
Sample.
sample.
Okay, so that's my suggestion. This is something that I'm not very used to, but I know that it's becoming very popular. There's this thing called hierarchical models, which is a kind of Bayesian analysis, where you have this hyperprior, then you can pick for this hyperprior one value for each of your data sets. Like you can use this prior on the slope to sample for each of your galaxy one different slope. And doing this in a hierarchical way, you can model all your galaxies, assigning for each galaxy a different slope parameter. I can send some.
But you are saying for which slope? You're meaning that for the slope of the brightness profile, of the slope of the density profile.
To all of them, you can assume a hyperprior and then sample for this hyperprior.
For the brightness profile, I don't know if something that Renan can do or not. Would be interesting if we have the value estimated for the brightness slope. It's be more interesting if you had the value for each object. Then you have like a sample from a prior. From the mass density, I question how much we would gain with that, because the mass density is quite restricted to 2, because we are working with, we are considering that the ETGs are Cs, are singular isothermal sphere. So I don't know how we would, I understand what you say, but I don't see how it would like go very beyond that value of the central prior.
Yeah, I mean, all my comments regarding this is because I'm not sure about this bulge halo conspiracy. I mean, in my opinion, and this is my opinion, and there are some papers in lensing showing that assuming a power law is not a good thing to fit your data. You may have introduced some external shear and other things, because this mass profile, this power law assumption is not a good assumption. You don't have enough complexity in this mass profile to accurately reproduce. So this is why I'm making this suggestion of hierarchical modeling or trying different things before we move on, because I think that our assumptions could not be the better assumptions regarding the mass profile, for instance. I know for now we are doing a great job in working with what we have in terms of data, but can we do better? That's what I'm thinking when I'm saying about the hierarchical modeling, or trying to use different profiles, if this is possible, to see if we really have something different. Because maybe our assumptions about power law profile, bulge halo conspiracy, or constant entropy, the same for all the galaxies, these assumptions could not be the best assumptions overall. And I talked too much and I reached anywhere, but that's it. Sorry. we are not ready.
Sorry, I turned it off to save energy and then I forgot. Just coming back to the comment that David made, not wanting to derail too much from this idea, but perhaps it is connected with the fact that well, maybe power law just trying to see how the mass distribution goes and maybe defining a system that would allow us to kind of nail this more more precisely. So this is the idea of going to these galaxies. I was not here for Felipe's talk, so I don't know. Is the worry, you gave a talk earlier, right? Yeah. So what you showed was an arc closer to so it kind of meddles a little bit with the distribution, with the distinction between the bulge and the disk and all that. Is that the worry? I mean, is the interest in going to a mass distribution that allows you to, I mean, the detection of a lens that is sort of further out, is the idea to just concentrate merely on this dynamics and not, I mean, I don't know.
Beleza, não? Tá bom, então. Tá, eu não. Poderia repetir um pouquinho em português só para. Meu ouvido em inglês não é tão bom ainda. Não tô tão treinado.
Não tem problema. Voltando aqui a, aos caveats que podem estar atrelados a como a gente ajusta, enfim, o perfil de massa, enfim, a distribuição de massa, que eu entendo da sugestão do Davi, falando de utilizar mais galáxias disco, onde tem um Einstein Ring maior, que não como o caso que você apresentou, aparentemente, que era um arco mais.
Eu acho que o microfone do Felipe morreu. Não sei se é só para mim.
Dá para ouvir agora? Tá. No caso do meu projeto.
Por isso que eu falei, se está funcionando. Olha aí se está vendo, tá?
Tá, então no caso do meu projeto, a gente está usando um sistema que tem um arco que está sendo lenteado, ele está próximo ao bojo, mas não está exatamente, não está imbuído ao bojo, ele não está muito. Ele não está próximo o suficiente para que seja impossível distinguir. A gente consegue distinguir. Claro que se fosse um pouco mais distante seria melhor. Dá para diferenciar. O que pode atrapalhar, às vezes, é o disco da galáxia, se tiver muita poeira. Então, no meu caso, eu vou usar uma imagem no infravermelho próximo, que é menos sensível à poeira, então eu consigo separar melhor o arco lenteado e subtrair da imagem original. Eu consigo fazer esse tratamento. Eu não sei se era.
Comentando aqui, na verdade, essa é até uma questão que eu queria conversar mais com ele, ainda não conversei ainda para entender os detalhes aí, até onde está indo essa medida do ar. Mas o problema de ir muito próximo do bojo, né? É justamente porque o bojo, em geral, um bojo usual, né, ele não tá no disco propriamente, né? E lá é dominado por dispersão de velocidades. Então você vai continuar se você for usar lentes para medir só o bojo, você vai continuar na mesma situação antes das elípticas, que você vai continuar tendo problema com dispersão de velocidade. Agora, se, por exemplo, tem uma galáxia, infelizmente, como vocês sabem também, uma galáxia, as galáxias mais massivas são justamente aquelas que usualmente têm os bojos mais pronunciados. E são também aquelas que são melhores para lentear. Então tem um problema, atrapalha. Agora, se consegue uma galáxia, por exemplo, que tenha bordo desprezível, tá? Que normalmente elas têm um mais baixo, mas e que tem uma arco de Einstein com um raio bom, isso ajudaria. Seria. A ideia toda é que aí não precisaria das equações de Einstein, seria o ideal, né? Bem, enfim, mas a questão dele que eu estava discutindo com ele é justamente até que ponto está indo o raio. Mas de repente é melhor ele me mostrar depois, não sei se quiser também acrescentar com algum comentário, né? É que não ficou muito claro assim o quão longe está indo, né?
Sim.
Tá. Aí depois você mostra que esse foi o caso. Não sei se tem comentário no chat, por acaso.
Queremos bulgeless galaxies. Lenteando. Eu não tô com.
Bom, só um comentário que agora, nesse momento, online, são todos falam português. Se vocês tiverem mais à vontade de português, bom, fiquem à vontade, né? Mas só para ler o que o Carlos escreveu, ele falou só para dar uns números, ele deu uma olhada aqui. O raio efetivo do bojo é 0,26 segundos de arco e o arco é cerca de 89 segundos de arco. 0,26, raio efetivo do bojo, 0,89 o raio do arco, só para ter uma ideia. Bom, so I'm lost in which language to speak. So anyone speak what they are okay with. That's no problem. But I think everyone follows at least English. So so one of the points that have been raised is maybe to look for further spiral galaxy lens systems, right? And I think that's an interesting point that may join many of the things we will hear during this meeting. On the one hand, there is this way of testing gravity, of course, and maybe you want to seek new systems. We have this large we have a compilation in the literature, the swells, which is the one from which Felipe has taken his sample, that has a nice light curves. So I have a question to Felipe about if you or Christina know of other systems beyond that one that have both arc and the light curves, because the swells, it's a like late type galaxy sample. So, and you pick one system. Are others that have already light curve, or is this the only one? David?
If I remember, there is. I can remember now one system which was studied in another project, but the system I'm using is it's good for my purpose because of its inclination too. It's 80 degrees, it's edge on, so it's nice to measure the rotational velocity. I can remember other systems that are so good too. Yeah, now I can remember.
Okay.
I can make a comment.
Yes.
Comment, Christina here. Yeah, we have looked into the literature and we found those systems are only swells. They have all the data that we need. But definitely we need more samples, and the sample we are creating in CBPF would be great for that, especially now that you are tagging all the systems. So maybe you have more data or more or other candidates to ask for follow-up for that in the future.
Yeah, I think we will find new late type galaxies after the last Beru inspection. There is one of the tags that we will put is I mean, that's already there. It's about being a spiral galaxy. So yes, I think we may identify new systems. We know that some are not on the swells and do look like late types in Das Peru. So I kind of optimistic we'll find new systems. So I think two things that we connect a lot with this meeting. One is, yes, should we follow up those for having light curves? Yes. So what do we need? What kind of data? Like in the CAC data, CAC is quite unique instrument, right? And we don't have access to it, but we do have access to Gemini. We can make integral field unit with adaptive optics, spectra, or maybe even single slit. I don't know, with adaptive optics also, at least you gain in the direction perpendicular to the slit. No, in the direction of the slit, you gain a spatial resolution. I don't know. The question may be to the people acquainted with that. What kind of instrument should we use to get new light curves? And what are the constraints in terms of angular scale and maybe brightness? Can we define like a sample to follow up for light curves? What we need for that?
By light curve, Martin, you mean rotation curves?
Pardon?
Yes, sir. You mentioned light curves.
Yes, sorry, not light curves. Yes, yes, rotation curves. Yes.
I have to check I believe with Gemini we have many instruments that we can use for that. As far as I know, we can use it.
Well, we have to measure H alpha for these galaxies. It should be, I mean, probably hydrogen will not be that useful in this case because hydrogen goes to much far, neutral hydrogen, I mean, and it will go to much far away. And I suppose that the, how to say, the Einstein ring, will not be that far from the center of the galaxy. So H alpha perhaps will be sufficient. I think there is already one discussion. I think you use H alpha. Oh no, H alpha. H alpha. Yes, yeah, yeah. It should H alpha should be sufficient. I think because neutral hydrogen is very important for the dynamics of the galaxy to be welcome to improve the internal dynamics. But as a good start, H alpha would be sufficient.
Okay, so perhaps we should have a spectrum of that object, coarse grained, maybe, I don't know, with SOAR, some spectrum where we have to check if there is prominent H alpha lines, perhaps, if they follow in the right part of the spectrum, and then seek highly spatially resolved spectroscopy. I guess maybe with adaptive optics, just to be able to differentiate between, make radio beams, right?
Yeah, I don't understand about adaptive optics in detail, but you understand better than myself.
So maybe that's something to think about once we start finding these systems is if they are suitable for follow-up. Maybe that's an interesting project. I recall that was also a project that was sort of emerged in this kind of discussions in the previous meeting about doing follow-up with SOAR, and then we did, and we have the results, and I think that was very nice. So yes, we can come up with the idea of making a follow-up now, targeting more like spiral galaxies, right? The other point that I think maybe is interesting to discuss is that, like I think Felipe mentions, like 10% of the lenses are late types. So when we train machine learning algorithms to find the systems, we know that of course the machine learning algorithm is as good as the training sample. And if the training sample is biased or doesn't have some type, you will not find it, right? Or maybe you find with a less efficient way. So I think most of the simulations that I am aware of, the simulated samples, are only late type galaxies. I don't know if there are simulations. No, early type galaxies. I don't know if there are simulations with late type ones. And when you do further training in like fine tuning or anything in the real data, then if you use the whole data set, it's not balanced in the sense that you have more early types. So maybe that's something to think about, like when we think about automated classification using, CNNs or whatever, we should have maybe training samples that look for spiral galaxies too, right? Yeah, I don't know if anyone can want to comment on that.
I guess the main difficulty with this is modeling the spiral galaxy. It's not hard to simulate strong lensing using a spiral galaxy. It's hard to get good parameters of that galaxy that would affect other things in the simulation. So the real issue here might be an issue on my part for not knowing how that works, but the real issue here is the modeling of the lens galaxy, the spiral, the velocity dispersion in the lens galaxy. So as far as I'm aware, yeah, no simulators do spiral galaxies as deflectors. So I don't know, for the future, I think that we're not looking that far yet. We still need to work to get it to work with early types, and then when we have a solid understanding of what is going on with early types, then we can try to work with the late type galaxies.
Yeah, so one point is that LSST is expected to find 100,000 systems, right? So these numbers are always kind of tricky because it's like 100,000 systems with an arc, maybe, or 100,000 systems for which I can find a good lens model that is useful for science. These numbers are big and tricky, but let's assume that is 100,000 or maybe 10,000 strong lensing systems, and 10%, only 10% are spirals. Still is 1,000 or maybe even 10,000. So comparing to the small samples, that's something that has a potential of increasing a lot, right? And as it seems that not enough attention has been given to those types of lenses. So that's something we may think about. I mean, I think in this team, what I like about this group is that we can go from the very theoretical motivation of taking specific modified gravity, which is nice, but also as we've been discussing, maybe we are not probing modified gravity at all, but looking to this new data that helps a lot, right? I think my side, I'm few sort of cosmologist yet still. So I like this. I find it, sexy trying to find test modified gravities, like, but I think I am aware we may be not doing that. In any case, having new data, new high quality analysis, doesn't matter if you have modified gravity or not. It can be used for many things, right? So I think what I'm saying about this group is that I think from one side we seek data, better data, better analysis. And on the other side, we look at, of course, theoretical motivations, which is, I think, the two things have to go together, right? But so investing some time about the modeling and the finding and everything about these late types may be an interesting thing to think for the future, right? So
I was wondering when we talk about, I was actually trying to look at the adaptive optics instruments on SOAR and Gemini. But this is when the rotation curves that you're relying on then usually are H alpha. Is there a need for H1 to actually go beyond? Is there a need? Because I would estimate that you need to go out to get a better handle on the mass distribution. You would need H1, but no, usually is H alpha sufficient?
The point that H alpha is useful for describing the rotation curves in the inner radius region. So it's the best tracer for the inner radius. But for larger radius, you need the H1. And it's much better than H alpha when you go to out. So in general, to have a good modeling of the cinematics of Galaxy, it's good to have both of them. This is the idea. But since this lensing should not be, I don't expect to be very far, for instance, like up to the last observed rotation curve in the H1. I think the Einstein will not, I don't expect to find an Einstein ring it's so large. So H alpha perhaps should be, at least a good start. Indeed, if you have both of them, it would be better because we are improving the cinematics.
So I was wondering because you were suggesting looking at these Einstein rings further out, but there is a certain difficulty in actually matching the H1 rotation curves and the H alpha. So there's always something kind of weird happening in the connection between these two. So
Yeah, as far as I understand, that it's not that always they perfectly match everything. Is there is some doubts also because H alpha also clusters. It's more clustered, so you have to take some average. There's some subtleties, but as far as my understand, that usually they go reasonably smooth. There's but okay, for instance, for sure there are some individual cases that they don't match well, but my understanding is yeah.
the most greatest difficulty has been actually a molecular H2 and H1. So maybe this is, but it would seem that these are the scales that are being probed right now, right? So if they're like 0.84 with respect to a 0.20 something arc second of a bulge, that's pretty close to the bulge. But anyway, I was trying to disentangle how well we need to know how internal is this internal rotation curve that we need to what.
Good point, because Carlos present this data about the arc of second, but this data alone is harder to say how good it is because it's good. You have to compare some scale net of the galaxy. For instance, if you have the data of the disk scale length, for instance, so because after all, or at least a conversion to kiloparsec, because it say a fraction of arc of second can be anything. It depends on the distance and also also compare the disk scale length. Because for instance, if it's about one disk scale length, then okay, then it's already a good measure. But it's about 1/10 of a disk scale length, it's nothing.
So on the I was going to say something I forgot. So on the just to say that this analysis that we are doing, like most of things we heard up to now, is like take a bunch of systems, measure one spectrum, measure one lens, and model that single spectrum and that lens, and just get a lot of them. Most of what we heard today was about that, except Felipe, which is one system with a light curve, or Carlos, which is one system with the velocity dispersion. But just to say that this analysis that we are doing, this coarse-grained one with a lot of systems, people have been using the literature for other means, right? People just assume that gamma is equal 1. I mean, they don't touch this GR, and you can measure the cosmological parameters and other stuff like curvature. So I think we should also keep an open mind. Maybe I'm not very interested on that because I think we can measure omega lambda and omega m in a much more precise way. And what is interesting about these small scales is this rather unique way of measuring gamma. But anyway, I think we should keep an open mind and especially to be aware of the literature because some of the energy that was put into understanding these kinematics, these systematics, maybe was in a different subject, but very similar data. So you also have to look at what people have been doing beyond gamma in terms of systematics, right? But okay, so we discussed that systems in more details, like IFU data, or maybe switching systems like spiral galaxies, looking in more detail, thinking about these systematics. What about other possible observables? I think Eduardo mentioned time delays. Do you want to say something about that?
Time what?
Time delays.
I mean, time delay is an increasing pop star. because it's the main use for cosmology. So I mean, it's probably a good road to us to pursue our group of CBPF.
Right. So okay. That brings us to the discussion of after, not today, about the time delays, like time domain. What we will hear about time domain, LSST. I think everything we did so far is static lenses. And I think we can make a lot of discussion on the time domain. So one thing is that like time delays, they also depend on the sum of the two potentials, like lensing, because it is lensing. So it is null geodesics. It's the same simple physics of null geodesics, but it's a new observable. So maybe subject to different systematics, like the arcs. Usually what we measure about the multiple images are connected to the second derivatives of the potential, like the magnification, or maybe the first derivative of the potential, like in the position of the images. And time delays is no derivative. It's the potentials themselves. So there may be complementarity ways of removing systematics. So that's something which maybe it's useful to have in mind. But let's discuss that. I think we are almost time for lunch, so that's good. But just throwing this. Okay, so in a more maybe logic thing, let's ask who believes general relativity is right, and who believes we should may have some either modify gravity, any modify gravity for dark energy, or whatever, GR or anything else. Vote.
I believe we should not believe.
It's not about believing.
The word is like that because it's full of atheistic.
There wasn't a saying, there was something like all models are wrong, but some of them are useful, or something like that.
Right. Yes, I mean, I think people have their own beliefs, but we shouldn't be guided by them, right? It's not easy, but yes.
Português?
Pode.
Então, Martinho, eu tenho uma dúvida. Pode ser uma dúvida boba, mas você sempre tem, você tem uma balança nesse tipo de análise, digamos assim. De um lado você tem matéria escura, de um lado você tem gravidade modificada. Se aumenta um, abaixa o outro, aumenta o outro, abaixa o outro. Pode ser visto dessa forma, né? Mas eu queria saber se não tem uma forma, pelo menos com galáxia elíptica, de você restringir a massa de forma independente, só com, por exemplo, alguma relação massa-raio, algo tipo Tully-Fisher, não sei, tipo galáxia espiral, não sei. E eu queria também saber se você usar lente e galáxia dinâmica, você já não conseguiria restringir já conseguir dar um constraint nessa balança, né, digamos assim. Porque parece que, assim, vendo de uma forma meio naiva, assim, esse tipo de análise parece que a gente está sempre perdido, trocando seis por meia dúzia. Igual da própria RG, né? Você passa pro lado esquerdo, passa pro lado direito. É massa, é geometria, é massa, é geometria. Parece que fica uma coisa meio ambígua. E aí, basicamente, essa é a minha dúvida. Talvez o Davi saiba.
Eu não sei se entendi completamente a questão, até porque você falou também de Tully Fisher, eu não entendi por que só pra eu
Não,
entender
eu
por que
misturei um monte de coisa, mas basicamente como é que a gente pode separar as coisas direitinho? O que seria gravidade modificada? O que é matéria escura?
a
Porque,
minha
por exemplo, no meu tipo de análise, às vezes eu penso assim, eu tô colocando uma praia isotérmica e eu tô achando um valor lá de energia escura, que na verdade é uma matéria escura entre aspas. E aí, para mim, eu já vejo isso como um bias, entendeu? Eu tô fixando a matéria escura e achando uma coisa parecida com a gravidade geral.
Não, é um viés, eu
É um
concordo.
viés.
Né?
Mas e aí eu queria saber se o Martin sabe me responder se você usar a dinâmica de galáxia junto com lente, você consegue dar um distanciamento dessa correspondência, digamos, se dá para separar.
Não.
Ou não é totalmente?
Assim, a ideia é que quando você usa lente e dinâmica, né, você ajuda, né? Porque se você usa só dinâmica, né, você tem tem mais possibilidades, entende? Você está só testando, só ponto de realidade geral, você está testando só um potencial, quando você usa só dinâmica, tá? Só a parte temporal. Quando você usa dinâmica e lente, você está testando mais coisa. Então é perfeitamente possível pensar num modelo que funcione só para dinâmica, mas não vai funcionar para dinâmica e lente. Tá? E isso é perfeitamente possível. Isso, não é difícil imaginar modelos assim. Tá? Então, ou seja, quando você coloca dinâmica, quando você coloca lente, você está acrescentando uma coisa a mais. Então, tá nesse sentido de, olha, estamos testando mais, estamos tendo mais informação, estamos, de repente, diferenciando, eliminando algumas possibilidades, por exemplo, se só de grafos modificados você pode eliminar, ou alguns átomos exóticos, não sei. Ah, mas na prática, assim, realmente, a gente tem essa divergência do que se é gravitação modificada ou se é matéria escura. E é um problema em aberto, não tem. Essa é a questão. Mas aí o que eu acho, assim, é bom você pesar. Tem essa questão do peso. Como é que você faz esse peso, né? E tem um lado subjetivo, que tem também, então, também você pode pensar bayesianamente, tem um lado subjetivo, mas assim, você vê pelo conjunto de evidências que tem, tá? E pelo que seria uma hipótese mais exótica, por exemplo, gravações modificadas, é difícil encontrar uma gravação modificada, você diz, essa daqui está muito bem motivada, etc. A gente, igual como a The Host que você apresentou, né? Assim, claro que é um panorama amplo, legal que você não tem
Embarca
uma
tudo.
motivação específica, né? Você pega uma grande gama, né? E vamos testar isso daqui, eu acho perfeitamente válido. Então, assim, no contexto de The Host, eu quero estudar The Host. Então, você está entrando nesse detalhe, você está explicando tudo, está explicando, isso aqui funciona assim, assim, assim. Agora vamos ver as consequências. Temos de fazer algumas hipóteses, como, por exemplo, tem que fazer essas hipóteses, o ponto-chave, entendo assim, tem que estar ciente que essas hipóteses vão gerar um viés para a sua resposta, tá? Tem que estar e ser honesto a falar, tá? Já tem até essas questões. Mas tudo bem. E de forma geral, sobre um estudo geral sobre dinâmica e lentes, eu acharia mais natural fazer primordialmente visando vincular perfil de matéria escura. Dada a situação atual de falta de suporte para geração modificada, eu acharia mais natural fazer uma coisa visando matéria escura. Agora, se você faz um complemento dizendo, olha, se enquadrarmos isso como gravitação modificada, essa teoria é favorecida. Eu acho perfeito. Perfeito, ótimo. Mas, eventualmente, essa que é favorecida vai ter outros problemas também, tipo, vai violar o sistema solar, por exemplo. Tá? Então, enfim, mas por mim, assim, é aquilo que eu estava comentando antes, que assim, que eu acho mais natural, quando você vai fazer um teste geral de juntar essas duas coisas, pensar, estou testando algo. Eu acho, de novo, com ponto de partida. Mas agora, se o ponto de partida é, eu quero estudar essa teoria de gravação modificada, vamos ver quais são as consequências dela. Tudo bem, não tem. É só uma questão de ponto de partida. Então, eu não sei se.
Não, acho que entendi, sim. Mas eu ainda fico com dúvida como é que você estudaria só matéria escura com esse tipo de análise. Como é que você mediria a massa luminosa independentemente, assim? Aí é uma dúvida que eu fico, assim.
Bom,
Posso?
primeiro,
Perdão, vai, Karine, primeiro.
só uma, acho que curta aqui, porque o mais que me pegou quando você está falando é a parte observacional também porque não trabalho tanto diretamente com lentes, então quando eu penso na distribuição de massa das galáxias, não, eu pensaria, enfim, tem, por um lado, sim, as rotation curves, mas a presença de aglomerados globulares, as pessoas podem utilizar isso, só que em geral eles são mais dirigidos, essas buscas basicamente são observacionalmente são como fontes pontuais que são detectadas, atreladas a uma galáxia, mas quase todas as buscas elas são mais para galáxias disco que estão alinhadas, são mais fáceis de detectar, mas eles basicamente te permitem então ter um, um probe adicional de qual a distribuição da matéria, porque você está olhando para as dinâmicas, então tem bastante trabalho a Ariana Cortese, que ela foi postdoc aqui um tempo com o Clécio. Então, é o tipo de coisa que também pode ser utilizada, mas especificamente eu posso olhar, mas em geral as buscas são mais dirigidas para galáxias com disco, mas pode ser uma outra maneira. Eu penso mais em estabelecer qual a distribuição de massa e depois olhar assim o lente. Então, a galáxia lenteada dar esse extra, mas eu vou dar uma olhada para ver
Obrigado.
o que tem
Minha,
aí.
dúvida realmente era Early Type Galaxy, porque eu sei até que para galáxia espiral você tem até dificuldade com a questão da inclinação, né? Eu já vi muitos artigos criticando outros, falando, essa galáxia não tem matéria escura, mas é porque você mediu errado a inclinação, e aí parece que não tem. Ou ao contrário, já vi muito isso, entendeu?
Sim, bom, acho que já tivemos várias conversas sobre isso, Davi.
São comentários. Sim, você pode ter essas questões de inclinação, sim, mas isso é desprezível frente à incerteza de parâmetros de anisotropia. É,
Ah, é? Não
não, de
sabia.
anisotropia eu acho bem mais complicado. Não, porque a inclinação você vê a inclinação. Tá?
Aham.
Então você pode, só pode fazer um modelo mais, pode fazer um modelo melhor, pode de repente, igual, por exemplo, considerar que a inclinação varia raio a raio, em vez de ser constante, você modela melhor. O problema de anisotropia você não vê. Você está falando sobre como a velocidade está indo em direções que são inacessíveis. Então, assim, um- de novo, não é um parâmetro, é só uma função.
Sim, Carlos, você queria falar?
É só para adicionar, assim, rapidamente, a pergunta do Eduardo, é que, em termos de dinâmica e de lentes, a gente sempre tem acesso, ou a gente só tem acesso à massa total. Então, no fundo, o que a gente acaba vinculando é a massa total. E dada algumas suposições que a gente faz, a gente quebra a massa total em uma massa estelar e em uma de matéria escura, mas a gente tem que fazer algumas, né, suposições para fazer essa quebra. Então, no fundo, pelo menos assim, o que eu acho é que é bem difícil, utilizando lentes e dinâmica, ou observáveis astronômicos em geral, fazer uma decomposição muito boa, entre o que é matéria escura, o que é matéria estelar, e o que poderia ser energia escura, ou coisas disso. Porque, no fundo, a gente não tem bons observáveis para isso. Mas talvez o que responda a tua pergunta, ou ajude a responder, esteja em física de partículas, que é uma coisa que eu não sei muito, mas eu vi alguns trabalhos recentes que tem perfis de matéria escura que não seriam compatíveis com algum tipo de matéria escura específico lá da física de partículas. Então, se na física de partículas alguém conseguir medir uma partícula de matéria escura algum dia, isso eliminaria possíveis halos de matéria escura para a gente testar depois. Eu sei que é um chute muito longe, mas é porque eu acho que, em termos astrofísicos, é muito difícil a gente fazer essa separação entre as duas coisas e ter muita certeza sobre o que a gente está falando. Por melhor que a gente meça as coisas, a gente parte de um certo pressuposto, que em geral inclui dizer que tem um grande halo de matéria escura aqui, ou de alguma coisa, e se você olha em uma escala muito, muito grande, tu diz que esse halo é dominante, e tu pode desprezar a matéria estelar. Ou se tu olha num raio muito pequeno, tu pode desprezar a matéria escura e dizer que toda a matéria é estelar. Mas eu pessoalmente não sei o quanto que é possível a gente separar as duas coisas, e dizer que, ok, eu tenho muita certeza sobre as contribuições aqui do que é uma e que é a outra. É, não sei se exatamente uma coisa que a gente consegue fazer hoje com dinâmica e lente, sozinho.
Entendi. Valeu, cara. Obrigado.
Desculpa. Cristina, adelante.
Sei se tentar fazer um comentário bem rápido, só no que você falou antes, Karine, sobre usar aglomerados globulares também como traçadores discretos, né, para medir a massa. A gente já tinha pensado nessa ideia, até um dos projetos do Carlos para o doutorado. Seriam essas são fontes, né, mais são como fontes pontiformes, elas têm alto brilho superficial, a gente poderia medir elas. A gente tentou, teria o problema é que a gente consegue ver e poderia estudar a dinâmica delas só em casos a gente consegue ver esses aglomerados globulares extragalácticos até uma certa distância, né? Que seriam só para as lentes bem próximas. Por exemplo, aquela que o Collet estudou, que está no Redshift 0,03, algo assim. E mesmo assim, a gente já, no outro trabalho, tentou buscar os aglomerados dessa galáxia de Type, e são muito poucos, que já tinham dados até do Gemini, mas eram tão poucos que não dava para fazer uma análise suficiente assim da dinâmica deles para poder inferir a massa. Então tem muitos desafios observacionais. Nas espirais eu não tinha pensado, é bem mais fácil encontrar eles, até porque não estão tão embebidos, né, na luz como da galáxia, como nas orbitais, mas acho que tem esse problema da distância também. Fizeram um traçador que eu gostaria de adicionar esse problema também. Até para traçar a matéria escura como o Carlos mostrou, né, a gente não consegue vincular muito bem, justamente porque nossos observáveis estão em raios menores, né, onde ela não é tão dominante. Então, poderia traçar até raios maiores, mas acho que por dificuldades observacionais vai ser um pouco difícil no momento.
Ok, bom, acho que temos muito pano para manga para discussões. Acho que agora está na hora da gente parar para o almoço, mas teremos mais ocasiões para discutir tudo isso e muito mais hoje à tarde e também amanhã e também na quinta e também na sexta. Então acho que eu tenho várias perguntas que eu queria fazer para o Carlos, mas depois eu guardo aí para discussões. E então é isso aí, gente. Queria agradecer a todos, todas, pelas discussões que foram excelentes, pelas apresentações que foram excelentes, os trabalhos foram ótimos. Agora então a gente para, vai almoçar e a partir das 2 da tarde estamos de volta. Então pode fazer um aplauso coletivo aí para tudo que aconteceu. Só um detalhe para os participantes em pessoa, a gente aqui se preocupa muito com o meio ambiente, então o crachá, quando acabar o evento, lá na sexta-feira ou no dia que vocês não puderem mais vir, aí a gente devolve o crachá, o plástico do crachá para as secretárias, a gente pode ficar com um papelzinho de lembrança, e aí isso vai
So, hi everyone. Thanks for coming to our first afternoon session. In this session, we will have two talks and a discussion period after them. So our first speaker is William. Let's please welcome William.
Okay, hello everybody. So I'm going to be speaking today about investigating varying gamma ppn using strong lensing. So let me get started. Yeah, there we go. And so I'm going to give it a little quick word on the analysis that I used to get these results, and talk a little bit about how this is assisted by this kind of analysis is assisted by having a larger data set, and look at some different methods that I use to analyze the data, and then have a look at some of the results. So start off with the parameterized post-Newtonian formalism, right? So this is what eventually gives us gamma ppn. We have our metric described by a Newtonian potential and a curvature potential. And the slip ratio then is given by this, which I actually put the wrong way around, I think. But we'll ignore that for the time being. In the case where we have this, that the curvature potential is a factor of the Newtonian potential, this gamma ppn, then yeah, then the slip is the same as our gamma ppn. So why look for a gamma ppn, right? Why look for a varying gamma ppn? So the thing is, we can have a gamma ppn that evolves with cosmic time, right? So some of the theories, such as these dose theories, which Eduardo's talking about, can have a scalar field which evolves with cosmic time. We can also have a variation across different types of systems, right? That varies with the properties of the system, and this can be down to dark matter, where there's anisotropic stress, so we can have different amounts of dark matter in different systems, and if this has anisotropic stress, then we're going to have a variation of gamma across those systems. And again, if the scalar field is coupled to the matter in that system, we're going to have some variation of gamma across different systems. And also, of course, so many of the previous works, a lot of which we've seen today, show gamma ppn equal to 1. This may be just an average value across the whole range of systems. And so what are assumptions that go into this? Well, we assume, much like the other works, a power law for the density profile and the luminosity profile, and in this case as well, alpha and delta are taken to be constant, and a constant velocity dispersion anisotropy parameter. So again, now we use this equation here to constrain gamma, right? We have priors here on the alpha, beta, and delta parameters, these Gaussian priors, and gamma is generally with an unbounded and flat prior in this case. So explore the parameter space using MCMC, and oh, that's going the wrong way. And get our value for gamma. So how does a larger data set help us to get a deeper understanding, right? So thanks to Henan and compiling Last Baru, we now have a much larger data set to work with. And many of the reasons why this is better are quite obvious, right? We get smaller error bars. It's easier to look for systematic errors, since we can split that up and have a look in different ranges. We can compare between different subsets of the data, right? We might have data come from different places. We can have a look and see, are those consistent with each other? And finding variation with observables, as we're trying to do here. So the analysis carried out using Last Baru, so I'll refer to this Venn diagram. I might jump back to it a couple of times to clarify, since I'll be showing results from various subsets of this set. And so what I'm going to start with is looking at some of the challenges of using smaller data sets, right? So here's one example of analysis that's gone wrong, which is why the plot looks looks very strange indeed. So here, this thing here is the best fit line, right? Which of course is very bad. We're actually missing 3 points here. There's two of them that are down in the negative, and one of them that's a way up around 8.8. And you have a chi-squared for any of the models. So we have a GR model. We have a model where we're taking the gamma to be a constant and put it at the mean value of each of the bins, right? So this analysis is taken by assuming a constant gamma at different ranges of redshift, and you can see across here the number of systems that fall into each bin. So the point is that with these small data sets, we can get these stray results, right? Again, we can even try and shuffle around the bins to try and get those results back, try and increase the number of points in each bin, but still, you might notice here there is a point missing here, right? So this is split into 10 bins, and if you count here, there's 9 points, right? So there's one missing here, and this is a way off up around 3, right? So just keep getting these stray bins, whatever you do, and yes, so here's just another example with a different observable, right? So here's looking for the variation in Einstein angle, and it's very clear here with this point you get these very small error bars, which is of course this is another problem arising from the MCMC. So to summarize that, larger data sets allow for more options in binning methods. They allow us to bin the data in the first place. The smaller data sets can result in these anomalous values, bad fits, and these strange error bars, and being able to split up. So then being able to split up data sets means avoiding results which could come from an average value across the data set. And we can also look for systematic errors which may only be occurring in a specific range of the observable. Right, so 2 kinds of analysis were carried out for this study. So I'm going to have a look at comparing them both now. So we had one analysis where we had, as we've seen already, the bins split up, and here we're taking a constant gamma for each bin. And one where we had an extra parameter added on, right? So for the MCMC, we add in a gamma 0. We take gamma ppn to be gamma 0 plus gamma 1 times some observable, right? The observables which I looked at were redshift of the lens, redshift of the source, velocity dispersion, and the Einstein angle, right? So I look quickly here at the lens redshift. So you'll see here, this is the binned analysis for the lens redshift, right? And it's quite a nice fit, right? So then we have a look at the source redshift, and here you can see we've got a few little kind of points which are skewing away. You can see down here, these ones are these are a bad fit with the data. So I guess it's nice to get that little bit of detail that you're seeing with each bin. Now this one here shows not only the binned analysis, right? So this is for the one that we saw before that was wrong, where he had there's a few points away off up here and a few points away down here, and you can see here that even with the extra parameter analysis, right, where we have the gamma 1, this line that's predicted by that is skewed upwards. Now, whether that's a genuine effect or whether that's drawn up by these anomalous bins, as I call them, is a very Good question. You know, it's from the bin analysis, it may be more likely that it's been skewed upwards by these bins that are going astray. So this here then is with the full data set. And got a lot going on here, but I think the important thing to follow here is that it's very much in line. So this red that you can see along here, this is the constant gamma, and you can see that this is very much in agreement with the result for allowing for a varying gamma. And here's for the source redshift, and here these black lines you can see are these are the errors for the bin analysis, and here again you can see with where gamma is allowed to vary, again is very consistent with GR for the source redshift. And now, so the advantages from that anyways of the bin analysis is that it's easier to see if a small number of systems in some range is skewing the result, right? Like we had with the source redshift analysis that was there. And able to see how well the results for each individual bin fit the data, right? You have the little chi-squared graph along the bottom that can tell us about each of the individual bins, and if one bin which is skewing upwards, whether that's an actual better fit for the data or if that's just kind of a statistical variation. The advantages then of the extra parameter analysis are that it's much easier to compare between the models using the likelihood ratios, Bayesian information criterion, and the I always forget the proper word for that, but the AIC. There's no ambiguity on the size or the number of bins, right? So we don't have to trade off between the size and the number of bins to get the detail out of it, right? So through this analysis, we got found some results which showed a potential variation of gamma with theta e and the velocity dispersion. And this was identified most strongly, I'll say, in the full data set, right? So here we have the plot of gamma versus velocity dispersion for the full data set, and you can see down here the values for gamma 0, gamma 1, and the chi-squared for the fit. And the points here again are the bin analysis. So each with so over 280 systems, each of these have 28 systems going into each point. And here's for theta e, right? An even sharper slope. So again, we have and I think some of this has. Yeah, no, this is okay. So yeah, again, we have the gamma 0 and the gamma 1. So here we have the opposite direction here for the Einstein angle as a variation with gamma. And so we have here some of the statistics, right? So this first row here is for taking gamma equal to constant, right? You can see here the gamma 1 is equal to 0. And what we can do is we can look at the BIC and the BIC and the AIC here to compare the models, right? And you can see here particularly with the Einstein angle and velocity dispersion results, these values are much smaller than the constant gamma value for the BIC and the AIC. So this shows quite strong evidence, at least from here, for a variation. Although, what I'll do is I'll try and throw that into question, because here we have for the last Peru only analysis. So Well, I won't go back to the Venn diagram at this point, but I can go back at the end if anyone wishes to illustrate where this is coming from. And here we see much smaller, right? Almost no variation in gamma with the velocity dispersion, right? Although of course the error bars are much bigger. Here for the Einstein radius, again we see quite a steep variation of the Einstein angle with gamma. Although in this situation again is one of these where we have a bin that's missing, right? We've got a bin that's got a value away up there, and so again, it kind of throws into the question the result, right? Is this being skewed by this one stray bin, right? You can see here, like the majority of these, if you excluded the stray bin, you could say this is a pretty good fit with GR, right? Your furthest one that's straying is away up here, and you know that is not particularly far off, anyways. And here we have the statistical metrics again, and you can see here that the velocity dispersion at least is actually now greater than the constant. So the constant is very slightly preferred in this situation over the velocity dispersion, and the Einstein radius is still preferred over the constant gamma, but again we can kind of throw that into question because of the stray bins there. And yeah, so finally a bit of a conclusion is first that larger data sets mean we can get a more detailed analysis, better understanding of the systematics and smaller errors. And the type of analysis is important, right? So using this binned analysis and the extra parameter analysis allows us to get a bit more of a full picture of what's going on. And as for that, I think even what could be concluded from the discussion earlier is that some further investigation is required to make any conclusion about these results, right? And what they might mean. So yeah, that is everything I have for now.
Thank you, William. That was a nice talk. Does anyone have any questions?
Hi, William. It may be that right at the beginning I missed a little bit of the sample that you use because you seem to have a spread of redshifts. What sort of systems did you use in what redshift range? I actually couldn't see the numbers from here either. So
Yeah, so sorry, they're the early type from the last Peru compilation. They're all the early type strong lens systems. Early type
Galaxy.
yeah. And the redshift range was I think around 0.1 to around 1.5, I think, for the lens
And
redshift.
how many?
280 systems was the full
Okay,
full quantity.
Thank
yeah.
you. Thank you.
Any more questions?
Sorry, I cannot understand the models that you tested. I think it was slide 26. You present the results. Tw- 26. 20, there's a table with the results. Yeah. So, in the first line is the case of gamma ppn is a constant.
Yes.
Right. And then theta e is the Einstein radius, but
Yes. So sorry. So this is coming from here. So for the So for the Einstein radius, let's say took gamma ppn to be equal to gamma 0 plus gamma 1 times the Einstein radius normalized over the mean value of the Einstein radius across all the systems.
So, yeah, sorry, if you talk about it, this I didn't get. So, but what's the motivation for this normalization? For
Just to keep it dimensionless.
okay. Okay, so anyway, the interest that you find there is some evidence for the ppn to change.
Yeah, I get, yeah. So, I mean, yeah, as I say, I'm still not sure how much to trust the results, I guess, because, as I say, we have some of these, some of the subsets show very little variation, and yeah.
Yeah, but yeah, if you see this Beacon and Ike, they show some evidence, but it's the plot is not that clear. Yeah.
Yeah. Well, yeah. So this would be the plot that corresponds to these, this table here, these two plots corresponding to here and here.
Okay. Okay. Thanks.
Okay, let's thank William again. Our next talk is going to be given remotely. Is Prajoal in the session?
Yes. Hello.
Okay, so everyone, let's welcome Prajoal. Whenever you're ready, you can start.
Oh, okay. Okay. Very good. So I'll be talking about slightly different kind of lensing, with in the gravitational field of a soliton or let's say a black hole solution. This work is being done along with my supervisors, Davi Rodriguez and David Mota. And thank you for this opportunity for uh, allowing me to talk in those lens. To start with, what I'm looking at is what we can infer about can we constrain modified gravity theories by the recent black hole images and photon spheres and black hole shadow measurements. And so to start with, we started out with taking branch decay theory in vacuum. And as you all might know, in branch decay theory, we just replace the Newtonian gravitational constant with a scalar field. So in vacuum, the field equations turns out to be very simple. Of course, indeed, we can add a energy momentum tensor here as well, just to make it slightly more complicated. But overall, we have only three variables. One is the branch decay field. And taking the Ansatz metric, because we need a black hole solution, there are two more variables coming from the metric. One is the function A, the function B. We are looking for static solutions, so there is no time dependence anywhere. So we'll have three equations for these three variables from the equations of motion. And these three equations have more solutions, at least four of them. But we'll take one of these solutions, which is for one of these constants put to zero. There are other solutions for this to arrive at the black hole solutions, but because as you can see, if I put c equal to -2, the equations get very simplified. So I'll take this choice of C equal to -2. So with this choice, there are three solutions what we are looking for. The solution what we are looking for, this is the solution for the scalar field. And with A and B, we have the metric as well. So what is the nature of this solution? When we look at the Kreshman scalar, we plug this into the formula of Kreshman scalar, and we see that, okay, it really varies as 1 over r squared. So it does have a true singularity at r equal to 0. It also goes to it is also asymptotically flat. This you can see in this plot, where I've only plotted the function a, but you can also see it for function b. For large r, it turns out to be 1. So this all together goes to a flat metric for a very large r. However, the only difference comes for the point that it is a naked singularity because there is no minus sign here. So this is, I mean, also for omega positive. Omega is the branch decay parameter, and that is nothing but beta squared. And alpha here is again gravitational constant, is again one of the integration constants, which turns out to be the mass of the black hole, related to the mass of the black hole. So this is the only difference which it makes, that is, it has a naked singularity. So once we have this naked singularity, the first thing what I would like to test is that, okay, if I expand b, the function b, I'll get something like this. And I would like to see if well within r equal to bd, I have a branch decay solution. And away from, for very large r, it has to be asymptotically flat, right? So I want to check if there is this smooth transition between one metric to the another. So the way to do that is to compute the extrinsic curvature and see if that is continuous. First of all, our metric is continuous across this hypersurface. And now we'll have to check if that extrinsic curvature of this hypersurface is continuous as well. So this hypersurface has this metric where, as you can see, there is no r coordinate. It's the hypersurface of r equal to constant. And then we can compute the extrinsic curvature given the norm vector. And the point is, it is continuous. So there is we can have a smooth transition between one metric to the other. So there is nothing special happening for r equal to RBD. Okay, but there is a major problem when we come across naked singularity, or when we are dealing with scalar tensor theories, is that there are very established theorems, especially starting with Hawking, and also then later on by Ferroni and Rio, stating that branch decay black holes should be equivalent to those of black holes in general relativity. So Hawking proved this first for given certain criteria that scalar field is not diverging at some space-time at some points, and we have asymptotic flatness, and we are looking at static solution in vacuum or with electromagnetic fields. So, but later on it was generalized to scalar tensor theories, and so the theorem is like this. So branch decay black hole solutions are equivalent to solutions of GR, given that the scalar field is linearly stable, the scalar field does not diverge, and the scalar field follows the weak energy condition. So we'll have to check if all these three conditions are satisfied in the case of branch decay black holes, what we are looking at. So we see that there is linear stability because there is no potential in our action. So it is directly satisfied. And we can also check the scalar field also doesn't diverge for large R, and also for R goes to RBD. Of course, there is it does have some problems at R equal to 0, but we can exclude this point. And then we can also see that weak energy condition is satisfied. So there is, now we are stating that our solution of black holes, which we have found, is not equivalent to the black holes of GR, because GR doesn't, at least non-charged black holes doesn't say, non-extremal black holes are not naked, are protected by some horizons. So the problem is to state come to the conclusion, to the solution. I would like to just discuss about what solitons are. Let us take a general scalar field. The Lagrangian would look like this. Of course, it could also be a Lorentz invariant Lagrangian with the time derivative as well. But I would like to make things simpler. So let's consider static scalar field. The energy of this scalar field is this expression. So now say we have defined certain boundary conditions such that we are the second term. I mean, in this, I'm just completing the square. And here I want the second term to be 0, which is the boundary term. So let's say that we choose a boundary such that the second term is 0. And the minimum energy requires us to have this first term should be 0. And this equation is the soliton equation. And the solutions would look like something with tan hyperbolic, or in other, it depends on the potential. For example, if I consider a potential which is similar to Higgs potential, and H here would be something like in supersymmetry, it's the superpotential. But however, the point is we get a scalar field equation, scalar field solution, which is like tan hyperbolic. As you can see, it interpolates between x equal to from here to here, and you can also compute the energy, which is a static lump. And so the solitons are nothing but spatially localized particle-like configurations, which are stable. And and if I have to go back, we can see that our scalar field solution is also some sort of tan hyperbolic function. So given that, there should be some, it is actually proved in this paper that this solution is a soliton solution. And hence, the theorems which are which people have derived for black hole solutions in scalar tensor theories cannot be directly applied to such non-black hole solitons. That is why, even though all the conditions are satisfied, we do not get general relativity like black hole solution. So solitons are classically indistinguishable from black holes, but the difference comes at the quantum level. So what we are trying to look here is there a possibility to make to tell the difference by looking at the black hole shadow, or the shadow, or the shadow cast by the solitons. So in 2019, Event Horizontal Telescope provided us with image of M87, and later in 2022 May, we got the image of our own galactic center. So the dark spot at the right center is black hole shadow. Currently, the work has been progressed a lot. Now we also have what happens to the magnetic field lines and so on. But however, there are few important things in this image which could be used for tests, which could be our probes. The first thing would be the event horizon, which is the dark disk which you can see. For general relativity, it is of course the radius. Then we have which determines the photon sphere, which is the unstable radius of the photon. I say unstable because it is unstable only due to for small perturbation. You give small perturbation and it either goes in or goes out of the black hole. And then you have this dotted line, which is the shadow size of the black hole. It marks the kind of impact parameter of the black hole at calculated at R0. So with our soliton solution which we have, we can compute what should be the photon radius, the red circle which I showed. And for general relativity or the Schwarzschild black holes, we get the photon radius to be 3 GM. The major point is that for photon geodesics, there should be a maxima for the potential. So for the soliton solution which we have, if we compute photon geodesics around this spacetime, we do have a maxima. That means there is a photon sphere, there is a unstable radius for the photon orbits, and that is given by R0, this expression. So as you can see, the black hole sizes in if it were to be a soliton is considerably smaller even compared to the event horizon. It is almost half of the event horizon itself, let alone the photon disk size when compared to a Schwarzschild black hole. So these blue lines are the photon radius of the photon unstable orbits for soliton solutions which we have. As you can see, for smaller betas, you will get closer to GM, half of the Schwarzschild radius, and for larger beta, we'll get smaller and smaller. This is one of the things. The other thing is the looking at the shadow of the black hole by looking at the shape equation, where B is the impact parameter. For Schwarzschild black hole, the shadow radius is just square root 3 times the photon radius, photon sphere, photon circle radius. So here we choose Sagittarius A for comparison with observations. However, as you can already predict, it doesn't make any good predictions for given for the mass fixed of the black hole, because it is predicting smaller black hole, but that doesn't rule out existence of solitons or but it's just that this supermassive black hole may not be a soliton. So, however, we'll choose Sagittarius A, and we can see the deviation from the GR black hole through this parameter delta. And Keck and BLT telescopes already provide us with what has been measured already for delta, and that is given by this gray shade. Shaded area, which is the darker one is 1 sigma, and lighter gray is 2 sigma 1. The units here are this is the shadow radius in the y-axis with the units gm equal to 1, where I've set mass and g equal to 1, and in the x-axis I have beta squared. So as you saw in the photon disk for the photon ring picture, for small beta will have slightly closer to the observed values, but however, for larger betas, we'll get smaller and smaller shadow. So this is where we are. And now I think I would be open for the questions. Thank you.
Thank you, Prajwal. Any questions here?
Hello, Pajal. Thank you for the presentation. It was very good. I was a little bit confused about what is the soliton. It's the scalar field solution that is the soliton, or it's the Bronsted black hole itself?
So what we are claiming is that this black solution, which is not our original solution, which has already been in 1980s. So this has to be a soliton because it doesn't because there is a very strong theorem which states, given these three conditions, it has to be equivalent to GR black hole, which it isn't. But these theorems are not applicable for solitons. So that's the argument, that this has to be a soliton. And of course, this solution is a soliton solution. So this is a soliton.
Okay, thank you, thank you.
Any more questions?
So I have two questions. So one is, does well, when you compare like the predictions with the results from Event Horizon Telescope, since you don't have do you have an independent? Okay, let me rephrase. In our galaxy, we have an independent measurement of the mass, right? So we can have a prediction of the event horizon of the shape, the black hole shadow in GR, and we have the black hole shadow in Bronsted with your choice of parameters. Then you can compare both, right? With the data,
Yes.
current data, is it enough to compare the two?
I mean, I think we can compare. I'm still doing it. So what I'm trying to do is take the mass from the measurements of S stars around the galaxy and comparing it with the mass predicted by the black hole shadow. So see uh, if there are any constraints for beta squared. But it is still, as I said, I'm still working on it. Maybe by tomorrow or day after, I'll have it ready.
Thank you. Also, you mentioned KEC. Oh, KEC, you mean the S stars, KEC and VLT.
Yes, yes.
Thanks.
We have time for some more questions. If anyone has a question, either for Prajwal or for William, we kind of stepped into the discussion session, so please feel free to ask questions to either of the speakers now.
I have two questions for William. So you have checked independently for each variable if there is like a linear dependence, and apparently you didn't find any evidence of dependence, right? Do you think it makes sense to maybe you have the dependencies? Of course, there is some correlation between the three variables, right? Einstein radius, velocity dispersion, redshift of the lens, redshift of the source. These four, the four variables are not fully independent, right? They have a correlation, but in any case, you can think at least, let's say, sigma v, z of the lens and z of the source as independent. These three variables, you can think of them as independently. So could it be that in your sample, just because, I don't know why, you are canceling again some dependence, and maybe you should, I mean, the whole sample, right? So maybe, does it make sense to consider simultaneously a dependence on these three variables, Z, lens, source, and sigma V? Do you think you can take some information from that?
I guess it would make sense to have a look and see. Like I don't know. I guess it's quite difficult to extract any kind of meaning from the results. I think. So I guess it could be one way to proceed and see does how that looks. Yeah.
Thanks. Christina, I see you have a question. Please feel free to ask.
Can you hear me?
Mhm.
Can you hear me well? Okay. I was going to ask about the same thing as Martin, about the correlation on the velocity dispersion and the Einstein radius. But I have another question too. I noticed like a peak in your plot with the source redshift peak around gamma around redshift between 1 and 1.5. I don't think it's a small number of systems in those beams because the error bar is not large, but do you know what it can be? What do you have an explanation for that?
Sorry, could you say that again?
You have a peak in the plot where you compare when you're investigating the variation with the source redshift.
Yeah.
There's a peak in the value between 1 and 1.5 or something like that. Do you know why?
No, not really. I guess at the peak, that bin has a bad that value of gamma doesn't give a fantastic fit with the data. I guess the chi-squared is around 5 in that bin. That shows the peak. I know in some other of the smaller data sets that I checked with source redshift, that peak kind of gets diminished a little bit. So it's kind of hard to say. There was one moment where I was looking, that peak was kind of in a region where there was a wide spread of lens redshifts, but I kind of had a check of that, and there was nothing significant there. So I'm really not sure why that peak is there.
And with regards to the measurement, your velocity dispersion, the measurements in the sample that you used, all of them are, I mean, they are homogeneous measurement. All of them come from long slit or fiber. Did you take into account the correction to how the velocity dispersion was measured?
Yes, so yeah, the correction is taken into account in I believe in the equation in the first, I think it was the first equation I showed, this equation for the line of sight velocity dispersion.
Okay, sorry if I missed that. Okay, thank you very much.
I don't think I mentioned it when I was going over it, but yeah. Okay.
So let's thank both of the talkers again. We will have a short break now. It's 2:55, so 3:10. We should be back in 15 minutes.
Ingrid will be available to reply to questions after her talk. So I just ask people that are online to tell us if the sound will be okay when we reproduce it. Let's see. So we in the auditorium we cannot hear, right? E a gente não está ouvindo o som.
Boa tarde, eu me chamo Ingrid, sou estudante de mestrado em astronomia na Universidade Cipriano e agora vou contar um pouquinho sobre a minha pesquisa de mestrado, que é sobre a matéria escura e luminosa em lentes gravitacionais galácticas. Então, a ideia do projeto, ela surgiu a partir da pesquisa que quer testar a relatividade geral de Einstein. É uma pesquisa em colaboração com os pesquisadores do CBPF, e a ideia é analisar sistemas de lente forte entre galáxias, e é preciso fazer um modelo, né, modelar essas lentes, e obter um espectro das galáxias que agem como lente para ter as informações dinâmicas dessa galáxia. Então, tendo essas informações, é possível testar a relatividade geral de Einstein. Então, o meu papel nesse projeto era pegar as informações dinâmicas do espectro. E como eu teria o espectro, daí eu consigo tirar outras informações da galáxia também. E então, os principais objetivos para a minha pesquisa seria inferir a fração de matéria escura da amostra, fazer um modelo de distribuição de massa de duas componentes, sendo uma escura e uma luminosa, e estudar também as populações estelares dessa galáxia. E aí, testar a relatividade geral de Einstein também é um dos objetivos da pesquisa. Bom, eu creio que todo mundo aqui já sabe como funciona uma lente forte, mas então aqui é o esquema entre galáxias, a gente tem a galáxia lente, a galáxia fonte, e para testar a relatividade de Einstein, a gente vai modificar a métrica de Schwarzschild, acrescentando esse parâmetro gama aqui. Então, se a gente tem gama igual a 1, a gente volta para a métrica original de Schwarzschild. Tendo feito essa modificação, vamos testar a relatividade. Para isso, a gente precisa das medidas de massa de duas formas. Uma medida pelo modelo da lente e a outra pela dinâmica estelar. Então, a primeira forma, ela foi feita pelo estudante de doutorado João Paulo França e o Martin Markler, que são ambos da CBPF. Então, eles fizeram um modelo desses sistemas que a gente selecionou para encontrar a massa, e essa massa ela vai depender do parâmetro gama, porque como essa medida depende da luz, e a luz ela é desviada, né, por conta da distorção do espaço-tempo, então o gama entra aqui nessa equação. Agora, a massa medida através da dispersão das estrelas, né, da dinâmica estelar, ela não vai depender de gama, porque as velocidades dessas estrelas são não relativísticas. Então, através dessa dinâmica, a gente consegue inferir a massa sem precisar do gama. Então, a gente tem duas medidas de massa, uma depende de gama e outra não. A gente compara essas medidas e infere valores para gama. A minha parte, que foi, então, encontrar a dispersão de velocidades das galáxias. Como que eu consigo isso? Bom, as estrelas, elas estão se movimentando na galáxia, algumas estão se aproximando da gente e outras estão se afastando. Isso vai causar um efeito de blue shift e de red shift no espectro. Então, quando a gente pega o espectro da galáxia lente, nós temos as linhas de absorção dela, mas essas linhas elas vão estar alargadas por conta desse efeito, dessa dispersão das estrelas. E aí a gente consegue medir essa dispersão, que é importante para inferir a massa dinâmica. E esse movimento das estrelas, ele vai nos dar informação, então, da massa total, não só da massa estelar, mas de toda a massa que a gente vai ter ali naquela galáxia. Então, a primeira coisa que a gente fez foi selecionar as galáxias, né? Isso foi feito pelo Martim, pelo Eduardo. Isso, para selecionar essa amostra, foi utilizado a compilação que o Renan está fazendo, o Renan e o Martim. Então, eles selecionaram em torno de 30 galáxias, algumas foram observadas no primeiro semestre e outras no segundo, com o telescópio SOAR. Por quê? Nós temos outros trabalhos na literatura que testam a relatividade encontrando valores de gama, que a gente chama de parâmetro pós-newtoniano. Só que esses trabalhos da literatura, eles usam a dispersão de velocidades das galáxias observadas pelo SDSS. Então, a ideia desse trabalho era usar o SOAR para ter um espectro melhor, com uma razão sinal-ruído maior, e, através disso, obter as incertezas de dispersão de velocidade menores, o que iria impactar a incerteza de gama também. Então, esse era o intuito da gente observar com o SOAR. E aí, parte da amostra foi observada no primeiro semestre de 2022, e a segunda parte foi observada no segundo semestre. Eu fiz parte das observações, sou eu ali. Não fui para o Chile, infelizmente, mas foi divertido também fazer a observação remota dessas galáxias. E aí, então, observando, a gente pega o espectro. Por exemplo, nós temos aqui essa galáxia, foi a primeira galáxia que eu comecei a reduzir. A primeira coisa que a gente tem que fazer é posicionar a fenda para obter o espectro. Então, aqui esse risquinho vermelho seria a fenda. Posiciona de uma forma estratégica para conseguir os espectros que a gente quer. Aqui, então, nós estamos pegando o espectro da galáxia lente, do arco, ou seja, o espectro da galáxia-fonte, e desse objeto que aparentemente parece estar próximo da galáxia, mas talvez não esteja, está caindo ali na fenda também, então a gente vai obter esse espectro. E aí, quando a gente coloca, a gente observa isso aqui. O espectro que eu realmente quero é essa linha horizontal aqui mais forte, essa da galáxia lente. Os outros riscos são as outras coisas que caíram na fenda. Então, tem muita coisa ali me atrapalhando de pegar esse espectro. Eu tenho esse código de barras, que são linhas de emissão do céu. Tem vários pontinhos que são raios cósmicos. Então, para eu conseguir só o espectro, eu tenho que fazer a redução, aplicar várias ferramentas, né, para tirar essas emissões, esses raios cósmicos, tem que aplicar calibrações para obter um espectro mais ou menos assim. E aí, eu vou lá e seleciono só o espectro que eu quero, só a linha que eu quero, e aí eu obtenho algo deste tipo. Então, aqui a gente tem o espectro e ele já está sendo ajustado no código PPXF. Esse código, você pode selecionar uma biblioteca de populações estelares, de espectro de populações estelares. Eu utilizei a Miles, do Vasdeskis, e através dessa biblioteca ele faz uma convolução e ajusta o espectro que você deu. Além disso, ele vai calcular também o alargamento da linha de absorção através de uma parametrização de Gauss-Hermite. Então, eu uso o PPXF e ele me retorna os parâmetros de populações estelares e a dispersão de velocidades da minha galáxia. E ele tem esse nome de Penalized Pixel Fitting, porque ele ignora os pixels ruins. Então, aqui, por exemplo, dá para ver que tem vários riscos que eles não são do espectro da galáxia. Na verdade, eles são restos da emissão da linha do céu, do fundo, né? Então, na hora de tirar, ficou alguns pixels, só que para ajustar, ele ignora esses pixels ruins e ajusta só o que seria o espectro da galáxia mesmo. Então, retornando os valores de expressão de velocidades, eu fiz isso para a amostra toda. né, que a gente selecionou em torno de 30 galáxias, mas a gente observou 23 e 2 tiveram um espectro bem fraquinho, então, no total, 21 galáxias fazem parte da nossa amostra. E aí, obtendo a dispersão de velocidades, pelo menos metade desses valores tem na literatura, que são grande parte do SDSS. A outra metade não tinha na literatura, então são valores novos. E aqui é uma comparação dos valores que eu encontrei com os que tem na literatura. Foi preciso fazer uma correção para poder comparar, porque nós precisávamos de uma dispersão de velocidades do mesmo raio da galáxia para fazer essa comparação. Então, a gente aplica uma correção para comparar. E a gente pode ver aqui, o roxinho são os valores que eu inferi com as observações do SOAR, o rosinha do SDSS, e tem ainda esse dado de um artigo do LIF Emelha, de 2018. E aqui na comparação a gente consegue ver que, apesar da incerteza do SOAR ser menor em grande parte deles, em comparação com o do SDSS, por exemplo, tem alguns valores que isso não acontece. Por exemplo, esse aqui, mais acima a gente vê que a incerteza do SOAR é bem maior do que do SDSS. Então, o nosso objetivo de ter uma dispersão menor não aconteceu para todas as galáxias da amostra. E também nem todos os espectros da amostra tiveram uma boa razão de sinal ruído. Mas então eu consegui inferir todas as dispersões e eu dei essas informações para o João, porque aí ele conseguiu inferir o parâmetro gama utilizando essa dispersão de velocidades. Então, esse objetivo foi feito, e aí o objetivo seguinte, que são os objetivos principais para o meu mestrado, era, por exemplo, analisar a população estelar da galáxia. Então, o código ele retorna para mim a idade, a metalicidade e a razão massa-luminosidade estelar. E aqui eu consegui analisar a evolução da amostra da razão massa-luminosidade estelar, que a gente consegue ver que a razão ela diminui com o aumento do redshift. Esse ajuste é referente a esta fórmula aqui. Então, a gente tem que a razão de massa-luminosidade estelar em um dado redshift é igual a ela no redshift 0, mais um delta, que vai ser a variação da razão de massa-luminosidade. Tirando o log, a gente tem essa fórmula aqui, que é a que eu ajustei nesse gráfico. Então, o ajuste ele vai me retornar essa razão de massa-luminosidade estelar no redshift 0 e essa constante aqui que está multiplicando o redshift, que é a mesma coisa que esse delta log do ml. Então, esse valor que ele retorna, ele é referente à variação da razão com o redshift, né? E aí os valores que eu encontrei foram esses. Eles estão um pouco elevados em relação à literatura. Temos poucos trabalhos na literatura falando sobre isso, mas esse valor de 14 para a razão de massa-luminosidade estelar no redshift 0 é bem alto. Mas se a gente olhar aqui esse trabalho do Fontana et al., nós temos aqui, eles analisam uma amostra bem maior. Esses gráficos são similares, o que muda aqui é o tipo de estimativa que ele utilizou, então a gente pode focar nesse gráfico aqui de cima. Os xizinhos azuis são galáxias que estão formando estrelas, star forming, e as vermelhinhas são as early types. E como a gente está falando de lentes gravitacionais galácticas, a sua maioria tende a ser galáxias early type. Então, a minha amostra aqui tinha que fazer sentido com esses pontinhos vermelhos. E se eu pôr esse ajuste aqui, ele fica mais ou menos assim. Então, como a nossa amostra ela é pequena, eu não posso dizer que esse ajuste que eu fiz, ele representa todas as galáxias early type. Justamente porque a gente pode ver aqui que uma amostra maior tem uma maior dispersão. Mas a gente vê que as que estão formando, elas se concentram em razões menores, e as early type já tem uma dispersão maior aqui. Então, o que a gente consegue ver que nos dois estudos, nós vemos um envelhecimento da população estelar, ou seja, com o aumento do redshift, a gente tem uma razão menor, né? Então, com o tempo vai passando e a razão de massa-luminosidade estelar vai aumentando. Outra coisa que a gente pode inferir aqui, então, é a fração de matéria escura. Se eu tenho a razão massa-luminosidade estelar, eu posso calcular a luminosidade e encontrar a massa estelar. E como o João modelou a amostra, ele tem o valor da massa total dentro do raio de Einstein. E assim a gente consegue ver qual é a quantidade de matéria que está faltando entre essas duas componentes. E aí a gente encontra aqui, nesse lado a gente tem a matéria, o valor real da matéria escura, então essa massa que está faltando em relação a esses dois, com um redshift, e aqui é a fração, também com um redshift. O que a gente pode notar aqui é que a fração de matéria escura da amostra é, no mínimo, 50% da matéria total. Então, olhando para a amostra inteira, pelo menos metade da matéria dessas galáxias estão na forma de matéria escura. E o nosso último objetivo é modelar o perfil de densidades das galáxias. Então, nós temos esse perfil aqui como um perfil da massa total, e esse alfa, que seria o slope, se ele for igual a 2, nós temos uma esfera isotérmica. Esse alfa foi modelado já pelo João também, ele está escrevendo sobre esse trabalho, e a minha ideia é separar esse halo em um halo luminoso e um de matéria escura. Então, nós temos esses modelos, o de Ehrenquist para o halo de matéria luminosa e esse de Navarro-Franken-White generalizado para o de matéria escura. E a ideia aqui é encontrar esse slope da matéria escura e analisar a nossa amostra, para entender como esses halos são. E é isso. Muito obrigada.
Okay, now we have time for questions. I'm stop sharing. Let me see if they're running out. Okay, so since Ingrid is not there yet, so let's go directly to the next talk, and then we can ask questions to both speakers. There is a question? Okay, Chris, do you want to ask a question?
Yes, but if I can wait for
Okay.
this.
So let's wait. One of the reasons that she pre-recorded the talk is that she was not sure she was going to get in on time. So hopefully she will be available after next talk. So next talk is also a pre-recorded talk. Is by Eric Signaki, and it's investigating a pair of galaxy groups with strong lensing and dynamics. So I'll play his talk and let's see if it works.
Boa tarde a todos, meu nome é Eric Signaki e venho hoje apresentar o nosso trabalho intitulado Investigando um par de grupos de galáxias com lentamento forte e dinâmica. Trabalho este supervisionado pelas minhas orientadoras Cristina Fulaneto e Marina Trevisan. Começando com uma pequena introdução para o nosso estudo, galáxias individuais, grupos de galáxias e aglomerados de galáxias, todos têm relevância significante quando estamos falando da organização de estruturas do universo. Colocando o foco nas estruturas intermediárias como grupos de galáxias, percebemos que esses objetos agem como pontes entre o regime de galáxias individuais e os grandes aglomerados. Estudar a cinemática e distribuição de massa de grupos nos dá um melhor entendimento de como eles se formam e como eles evoluem. E, consequentemente, pelo padrão hierárquico de formação de estruturas do universo, podemos inferir como se formam os grandes aglomerados e até como a própria teia cósmica se forma e como ela evolui. Dado isso, nós estudamos o sistema Helm 18, um sistema que inicialmente foi detectado pela sua emissão no submilimétrico. Aqui nós podemos ver a imagem do interferômetro ALMA na banda 7, no canto inferior direito. nós podemos ver a disposição desses dois arcos de uma galáxia submilimétrica lenteada com um redshift espectroscópico medido em 2.4. Vemos que a distribuição desses arcos é um tanto quanto peculiar e, portanto, vamos ver sua contraparte óptica no SDSS. Aqui à esquerda nós podemos ver o que se acha inicialmente e, dando um zoom nessa imagem, podemos ver aqui no canto superior direito, nós vemos os dois objetos centrais. Sobrepostos com essa imagem também está os arcos do ALMA para a gente poder ver bem que há uma correspondência entre esses arcos e esses objetos centrais. Esse objeto vermelho é uma Early Type Galaxy, que nós vamos chamar de ETG. Esse é um dos objetos centrais do sistema RM18 e ele tem redshift espectroscópico medido em 0.6. Isso implica que o SDSS tem o espectro desse objeto e já classificou corretamente como uma galáxia. Ao contrário do outro objeto em azul, que foi catalogado como uma estrela, porém, devido à sua posição nesse sistema de lentes e à sua própria cor, nós chegamos à conclusão que poderia de fato se tratar de uma galáxia que foi corretamente catalogada, mais precisamente seria um quasar e por isso nós colocamos um QSO candidate ou um candidato a QSO. Reparem que cada um desses arcos está centrado em uma das galáxias centrais e a separação entre esses arcos é típica de um grupo de galáxias. Seria então o objeto lente desse sistema um grupo de galáxias? Para responder essa pergunta, nós definimos alguns objetivos. Primeiramente, nós queremos confirmar a natureza desse objeto, que nós chamamos de QSO Candidate, determinar quais galáxias fazem parte da estrutura que age como lente, determinar as propriedades do objeto lente, como massa, dispersão de velocidades, determinar as propriedades das galáxias centrais, propriedades cinemáticas, e determinar a probabilidade de interação desses objetos se houver mais de um grupo lenteando a galáxia submilimétrica. Então, se houver mais de um grupo, nós queremos saber a probabilidade de interação entre esses dois grupos. Para atingir esses objetivos, precisamos de dados espectroscópicos, e assim realizamos observações espectroscópicas multi-objeto usando o telescópio Gemini. Aqui temos imagens tanto do telescópio utilizado, o GEMOS, quanto do observatório onde o telescópio está localizado, que é o Gemini Sul, no Chile. Para selecionarmos os alvos para essas observações, nós utilizamos o catálogo fotométrico do SDSS e selecionamos os alvos de acordo com os seguintes critérios, priorizando de cima para baixo as galáxias nessa sequência vermelha, galáxias cujo redshift fotométrico está ao redor da ETG central, que é por volta de 0.6, e outras galáxias brilhantes no campo, independente da sua cor. E dessa forma, encontramos 76 galáxias que correspondem aos critérios que nós definimos. Ok, obtidas as observações brutas, nos cabe realizar a redução desses dados, de forma que eles possam ser devidamente analisados. No total, descontando os objetos que foram incorretamente catalogados como galáxias no SDSS, que na verdade eram estrelas, ou objetos muito fracos para a estação de um espectro, nós encontramos 70 espectros no total. Dentre eles, dois espectros que eram mais importantes, que é o espectro da ETG, aqui à esquerda, que podemos comparar o espectro que nós obtivemos com o Gemini em relação ao espectro do SDSS. Podemos ver que com o Gemini nós temos uma relação sinal do muito melhor, podemos encontrar e diferenciar algumas features que são importantes para defender o redshift, por exemplo. E nós temos aqui na direita o espectro da QSO, que claramente não tem o espectro característico que a gente esperaria encontrar numa estrela, mas sim numa galáxia. E assim, uma galáxia com uma velocidade de gás alta devido à largura dessa linha de H-beta, por exemplo, que vocês podem ver ali em torno de 7.750 angstroms. Perfeito, dentre esses 70 espectros, com esses 70 espectros podemos medir os redshifts dos objetos, e assim nós temos que selecionar quem deles faz parte dessa estrutura do objeto lente. Selecionamos então os membros dessa possível estrutura de acordo com o seguinte critério: o redshift tem que estar entre 0.596 e 0.608. Esse é um critério engloba um alcance de 3.600 km por segundo. E considerando que a dispersão de velocidade típica de grupo de galáxias é por volta de 150 a 300 km por segundo, é razoável entender que outras galáxias que estão longe desse critério já podem ser descartadas como candidatas a membros. No total, nós encontramos 21 membros, e aqui na imagem apresentamos a distribuição dessas galáxias no espaço de redshift. Vemos que aparentemente temos uma distribuição bimodal, e para quantificar, utilizamos o critério de Rosman-Valmer, que dita que se este valor de D para as gaussianas ajustada for maior do que 1, estamos tratando de uma distribuição bimodal, Neste caso, nós temos um valor de D de aproximadamente 2.1, de forma que nós podemos dizer que temos dois grupos de galáxias lenteando o mesmo objeto, cada um com sua respectiva galáxia central, com a QSO pertencendo ao grupo da frente e a ETG pertencendo ao grupo de trás, quando falamos da linha divisada. Ok, dado que nós sabemos que temos dois grupos, basta saber quais galáxias pertencem ao grupo da frente e quais galáxias pertencem ao grupo de trás. Para isso, utilizaremos dois métodos de agrupamento. Dentre eles, nós temos o método de agrupamento de M-Cluster e o formalismo, que é descrito por Willman no seu artigo de 2005 e que nós implementamos de maneira similar ao artigo de Munhoz de 2013. Após separarmos os grupos de galáxias e as galáxias e seus respectivos grupos, nós utilizamos o método GBE, o Gap Bioweight Estimator, para calcularmos a dispersão de velocidades. Enquanto o M-Cluster se baseia em um método de agrupamento baseado em modelos, onde nós procuramos um modelo que melhor representa os corpos no espaço tridimensional, o Willman é um processo interativo que vai descartando galáxias conforme vai se calculando novos valores de sigma, até que se chegue num valor estável de dispersão de velocidades e, portanto, essa seria a distribuição do grupo. Com o formalismo de Willman, nós encontramos um número... Tanto o M-Cluster quanto o formalismo de Willman encontraram um número de membros igual para o grupo da QSO. Seria em torno de 13 membros, então, portanto, eles têm a dispersão de velocidades igual de 197,5 km por segundo. Por outro lado, há uma diferença entre o formalismo de Willman e o método de M-Cluster. No formalismo de Willman, nós temos 8 membros e, portanto, nós temos uma dispersão de velocidades menor, de 143,7 km por segundo. Enquanto no método de M-Cluster nós temos 9 membros, então um membro é adicionado a mais. E nós temos uma dispersão de velocidades para o grupo da ETG de 242,9 km por segundo. Vale ressaltar que todas essas dispersões de velocidades são características de grupos de galáxias. Dado que nós sabemos quais galáxias pertencem a qual grupo, podemos calcular a massa virial desses objetos. Então nós estimamos a massa virial de ambas as estruturas, utilizando essa equação. Para o formalismo de Willman e para o M-Cluster, ambos concordam na massa virial, como esperado, da QSO de 9,6 vezes 10 na 12 massas solares. Enquanto para a massa virial do grupo centrado na ETG, nós podemos ver que há uma discrepância. Nós temos 3,4 vezes 10 na 12 massas solares para o formalismo de Willman, que tem uma galáxia a menos, e 8,6 vezes 10 na 12 para o método M-Cluster, que tem uma galáxia a mais. Certo? Todos esses valores de massa também são característicos de grupos de galáxias. Ok, com as massas em mão, podemos finalmente prosseguir para o modelo de interação, onde tratamos o sistema como um problema de dois corpos. Aplicamos o método descrito por Beers no seu artigo de 1982, assumindo que ambos os grupos começam com separação zero em t igual a zero, ou seja, no início do universo, e que eles estão se aproximando ou se afastando pela primeira vez na história do universo. Para o caso ligado, nesse sistema de dois corpos, nós temos essas equações de movimento, onde R é a separação entre os corpos, T é o tempo decorrido, V é a velocidade relativa entre os dois objetos, M é a massa total de ambos os grupos, ou seja, a massa dos dois grupos somados, Rm é a separação na expansão máxima ao longo desse tempo que é decorrido, e Q é o ângulo de desenvolvimento, que ele varia de 0 a 2π. Esse sistema de equações pode ser resolvido acrescentando duas outras relações, e as relações são essas, que são dependentes dos parâmetros VR e RP, que podem ser medidos, são observáveis. Eles são, respectivamente, a velocidade relativa ao longo da linha divisada e a separação projetada entre as galáxias dominantes. Aqui nessa imagem nós podemos ver que o alfa representa o ângulo entre os grupos e o plano do céu. Perfeito? Então nós conectamos essas equações de movimento com os observáveis e nós encontramos a seguinte relação. Aqui nós podemos ver as soluções das equações na linha preta. O que são essas soluções? Nós escrevemos VR em função do ângulo de desenvolvimento Q e o alfa também em função do ângulo de desenvolvimento Q. Nós plotamos as soluções para esse possível sistema parametricamente, então variando Q de 0 a 2π. Nós plotamos também o critério de ligamento de Newton, que é esse critério que vocês podem ver aqui no canto inferior esquerdo, em vermelho, além da velocidade relativa medida do grupo dessa imagem. É muito importante ressaltar que essa é a velocidade que nós medimos para o nosso objeto, certo? Aqui podemos ver que para a velocidade relativa medida, que é essa linha azul, há duas soluções para o sistema, ou seja, onde a linha azul cruza as soluções descritas pela linha preta, quer dizer que essas são as duas soluções possíveis para o nosso sistema, e ambas aparecem ao lado esquerdo da linha vermelha, que representa o critério de ligação de Newton. Ou seja, ambas representam soluções onde os objetos estão ligados gravitacionalmente. Isso significa que o nosso objeto só pode estar ligado gravitacionalmente? Não. Mas a gente pode calcular a probabilidade dele estar dentro dessas soluções através de uma integral nesse espaço de fase. Com essa integral, nós podemos calcular a probabilidade de interação. E para o método do M-cluster, nós encontramos a probabilidade de 58% desses grupos estarem em interação. E para o fórmula de Willman, probabilidade de 47%. Aqui essa imagem ela descreve o modelo de acordo com o agrupamento de M-cluster. A imagem para o agrupamento do fórmula de Willman é diferente e, portanto, nos dá probabilidades diferentes, é claro. Mas não acrescentaria colocar outra imagem aqui. Como os trabalhos atuais que nós estamos fazendo, estamos atualmente construindo um modelo de lente gravitacional com o objetivo de reconstruir a fonte e nos dar uma melhor descrição do perfil de massa do objeto lente. Para tal, nós estamos utilizando o pacote em Python o PyAutoLens de Nightingale, primeiramente modelando a lente sem esses parâmetros cinemáticos que nós derivamos até agora, para que após, quando modelarmos a lente gravitacional utilizando esses parâmetros, possamos entender as diferenças nesses resultados e ponderar sobre a importância deles quando fazemos o modelamento. Por fim, com os modelos prontos, podemos estimar as frações de massa de matéria bariônica e matéria escura desse objeto. Concluindo, então, como principais resultados desse trabalho até agora, nós temos 70 espectros de galáxias na região de Helm 18. Nós encontramos que, então, há dois grupos de galáxias lenteando o mesmo objeto para esse sistema. Encontramos que o número de membros para cada grupo é de 8 ou 9, dependendo do método de agrupamento, para o grupo centrado na ETG, e de 13 para o grupo centrado na QSO. Reparem que esses são um número baixo de membros, uma vez que nós consideramos fazer um modelo conjunto da cinemática concomitantemente com o modelo da lente. Porém, com esse baixo número de traçadores, nós resolvemos por optar por esse modelamento mais simples que estamos fazendo no momento. Certo? Também conseguimos como resultados as massas viriais de ambos os grupos, ou seja, para a massa virial para QSO de 9,6 vezes 10 na 12. E também para cada método de agrupamento, nós conseguimos duas massas viriais para o grupo da sentada na ETG de 3,4 vezes 10 na 12 e de 8,6 vezes 10 na 12, dependendo do método que se usa. Claro, e por fim, nós conseguimos também um modelo de interação entre os grupos, com probabilidade de 47 ou 58% desses grupos estarem em interação, dependendo do método de agrupamento que é utilizado. É claro que vale ressaltar que a possibilidade dessa interação pode afetar a medida da massa virial, uma vez que, se esses objetos estiverem em interação, a massa virial, os objetos não estão mais em equilíbrio virial, então, portanto, a massa virial pode ter um certo bias incluído. E, além disso, o próprio modelo de interação leva em conta a massa virial, então esse bias pode cair nessa medida, nesse sentido também. E é isso, então. Muito obrigado e estou disponível para perguntas.
Okay, now we will open to questions. Eric Signaki is there. I don't see Ingrid yet. So if you have questions for Eric. So I have a question, Eric. So you didn't show yet the modeling of the strong lensing modeling of the system. But what do you expect to use as a model? I mean, we see like two main lenses, which are the quasar and the early type galaxy, but you have a lot of galaxy group members and you have two plane lens, right? To have the lens in two planes. So what kind of model do you plan to use? Oh, we cannot hear you. I think you are mute. No, you're not, but yeah, we cannot hear. Yeah, we cannot hear you yet. You are not on mute, but
Hi, maybe I can answer that while Eric try to connect. Can I?
sure.
Okay, we are thinking of using like a pseudo isothermal elliptical model for each of the galaxies, plus a component of dark matter for each group, INFW or GNFW for that. Like this will be our first test for that to describe the system. Plus an external shear, so.
Okay. Are there more? Thanks. Are there more? Oh, Eric, did we hear you?
Can you hear me?
Yes.
Okay. To answer the question, I think I heard Christina saying about the NFW profiles. Initially, we are planning to use two NFW profiles to describe each of the groups, like the dark matter component, of course. But we are also planning to include two more components for each of the central galaxies, PIEMD, the pseudo-isothermal elliptical mass distributions for each of the central galaxies to account for any stellar contributions. And I think you heard me saying in the beginning of the presentation about the red sequence that we use to define the target galaxies. There was another red sequence of galaxies in redshift 0.4 that of course do not belong to our group. So but is directly in the line of sight. So we are planning to also add an external shear to account for any lensing effect that could occur because of these interlopers in the line of sight. That is initially, of course, if we want to try any other profiles for example, the dark matter component, we are going to try to see what yields the best result for our submillimetric galaxy, such as giving a galaxy in one piece, only one component, of course, because we know that both of the arcs have the same redshift and the same spectra. So we expect the object to be only a single object or a single source.
Thank you. More questions for Eric? So if there are no questions, let's thank again. Okay, so now we have time for discussions. You can still keep asking questions to the speakers, but the main idea is for us to, well, have fully open discussion or some suggested themes that we have here. So, but if you want to start like randomly to raise something.
So it's actually an idea, a suggestion, because as I'm seeing the work of João and Ingrid, it's like an end-to-end gamma PPN work. You collect the data, you treat it, and then João does the modeling part, etc., etc. But I mean the proposition of this work is to test the weak field metric, the gamma ppm, and you use as a starting point GR and its dynamics. Okay, is that right? In the modeling part. So I think maybe it could be used another approach that I don't see much in the scale of galaxies, is that you could use, for example, the dosed, like those dosed potentials of my work, for example, or any other scalar tensor potential, in the sense that these metric potentials, they depend on the distribution of mass. So it's actually a breaking of the strong equivalence principle. So I'm imagining maybe if modifying the code instead using GR, it could be used on this kind of scalar tensor theory. And for example, by doing a proposal to SOAR, instead of measuring ppm, it's an ad hoc modification. You could tell, no, we want to test this scalar tensor theory, which breaks the strong equivalence principle, which actually testing GR, a very principle of GR. So it's an idea. I don't know if it's good.
Any comments? Yeah, I'm wondering, so in this case, you write the genes equation in a modified way, right? Yeah, but I mean, in our case, we are with linear gravity, right? Weak fields. So at the end, yeah, we only need the weak field linearized equation for the non-relativistic matter, right? Cold dark matter, stars. So it would be equivalent to the modification of the Jeans equation. But my understanding is like in the cases where like the host theories end up being in the solutions you considered, it's like having a constant gamma, right? So at the end is like, it ends up being the same or not. Right. Right. So what you're saying is, if we don't have an isothermal model, then we write the Jeans equation. It has this derivative of mass term, like new mass term, because of the scalar tensor theories.
So I think the idea might be maybe dropping the dark matter profile. I don't know if it's a good idea, but it would be cool to see what actually what would be the result in the modified gravity part in the strong equivalence principle. I personally think it would break this conspiracy with the isothermal profiles, and you actually would measure some breaking of this principle in kilopascal scales, which is actually, I've never seen the literature, only on smaller scales, physical scales.
Right. So I understand that the difference between having a gamma and like a specific modified gravity theory, let's say with the scalar tensor one, you can only see the difference in if you have a non-isothermal profile. So you would like to go to more, larger mass lenses, maybe like the ones that Eric shown, which are groups. the problems I see with group scales, but people can correct me, is that usually you have more complexity in the lens, because you do have to consider a dark matter halo. I think there's no way out. You have to consider dark matter halo, plus the halos of the luminous components. But since you cannot have like each luminous component as a free parameter, you end up assuming something like a constant mass to light ratio or a power law mass to light ratio. So you end up having more degrees of freedom. If you have like a cluster where you have a lot of images, it's fine because you have more degrees of freedom, but more constraints. But when you are at cluster scales, you normally don't have more images. Maybe it's just an arc, and you have more constraints. So I'm not an expert, but I think usually there is this problem with the group scale lenses that they are complex enough to require more components, but they don't have a sufficient number of images to constrain all this. On the other hand, they are more abundant than large clusters for sure. So there is more statistics. So I don't know, maybe Christina may comment on that. Yeah.
Yes, agree with Martin about the group scale lenses. I'm very interested in working with that, but it's really hard to. First, we don't have a large sample of that, and we have more. We have this problem. We have less constraints, but that's why we can use the dynamics. But that was the idea of this work, this system Eric is studying. But we found out that there are two groups instead of one, which make it more difficult to investigate the dynamics, and they also can be interacting with each other. Yes, but I don't know. I missed the first part of the discussion because we don't hear William. So I don't know if I understand the point of when.
So the idea is actually, it's actually pretty simple. He's asking the question: what if we remaze analysis, but starting from another theory instead of GR? Because, for example, the theory I was utilizing, those theories, the case of those potentials, which breaks the strong equivalence principle. So it depends on the distribution of matter. By using, for example, even an isothermal profile, but with ellipticity, like João uses in his analysis, like with the SI model, I think it would still have a different result. It would not lead to that degeneracy that we saw, that conspiracy. So I don't actually know it will be the result, but it's an idea. I mean, it resumes to, let's gonna test the strong equivalence principle at kiloparsec scales.
Right. So if considering elliptical model solves your problem, then I think you have to work out the non-spherical Jeans equation. And so the non-spherical Jeans equation in this modified gravity setting, and then maybe you're happy. And you can do this with galaxy scale systems. That could be something. Or maybe you want to go on the other way around and go to massive clusters where you have a lot of constraints. And maybe, of course, there are tests of GR in clusters. So instead of looking at the kinematics of the galaxy, the lens galaxy, like Carlos did or like Colette did, of a single galaxy, you can measure the redshift of all galaxy member components and measure velocity dispersion of the cluster itself. So this is done in the literature. There are limits on gamma. So in your case, you want to do it, but with a given modified gravity theory from scratch. So yeah, I think you have to work out the Jeans equation, how it looks like. If you want to work it on a cluster scale maybe, or on a non-spherical setting, it's interesting. I don't think it has been done before. And phrase it the way you're phrasing, like it's a test of a strong equivalence principle. I think it's looks appealing at least. But if you show us the equations, then we can discuss. Yeah, it's a good idea. Any other comment about this in particular?
don't know if I got it right, but for instance, for this Weinstein violation that we also use in our presentation, as far as I know, I only know that the derivation is spherical symmetry. So if you go to some elliptical setting, yeah, yes. Just right. Everything you said, you are present in spherical. Yeah, but I don't know if there is some results in other geometry. Yeah, because it becomes much simpler spherical. Yes. So if once you change the geometry, yeah, and then starts other issues about if the galaxy is indeed that kind of elliptical is just a matter of projection, etc.
Okay, so either you look at this complication or maybe clusters. Right?
Really big. So it's not really constraining of these parameters.
I know an old paper by Pezzuti et al. I think that measures gamma that way, but perhaps there are some more modern things. I don't know. Any other general comment topic?
Just one of the things that I cut from Ingrid's talk was the mass to light ratio. If I understand correctly, then the mass is derived based on the dispersion, and then the luminosity was taken from the R band. Is that correct? Yeah. So I mean, the fact that the numbers were so different from what you expected. I mean, I was just looking at a few papers, and I mean, I'm always insisting on using the 3.6 micron bands, and I'm just looking more into the mid infrared. So perhaps just looking at a different band. I was wondering why specifically our band, if it's just availability, which many things, observational speaking, are usually done that way, but it could be investigated. I mean, bands that would be better tracers of stellar mass. So I just wanted to ask her, but I don't know if somebody here can or is interested in that. But I mean, that's something that my group is actually quite interested in, just looking at the distribution of stellar mass in different stellar structures. And what we use is the mid infrared. There's 3.6, 4.5 microns. So that really kind of eliminates even more of the uh, uh, giants and just really stick to the low mass stars that comprise the bulk of the stellar population of the stars. So it's a good way of mapping the stellar mass available. And yeah, just it's in at 3.6. It's even further. I mean, there's a really nice plot by the Gamma survey. They actually showed just how SEDs of galaxies just varying a bunch of things: stellar population, age, metallicity, etc. And you can actually see that the dispersion is very tiny in these bands. So you can change on many things about your galaxy, but the way that you uh, determine the mass, if you're only going to be based on one band, you can also do full SED fitting, but then you need many more bands for that. But it's just very useful. So the Spitzer data was, yeah. And there's, depending on the galaxies, I mean, the 21 galaxies that you guys looked at, I don't know if there's this photometry available, but and obviously with JWST it's possible to do too. Well, it's possible. You need to get the time, but maybe there is already some. I mean, just it seemed intriguing the values that were being found. So just an idea.
Yeah. So I don't know where are these 20 galaxies that we are using in the sky, but they're, yes, they are available from the south, but they may be in the equator. We carried out the VIX82 survey with Vista and CFHT WIRCam, so in the near infrared, on the equatorial stripe 82. And one of the reasons was to have stellar masses. But then Spitzer has observed there is SPICE, like Spitzer equatorial survey. So if this is in that band, we have lots of information. If not, but yeah, definitely, I think it's very interesting. I think it's in general very interesting to look at multi-wave band information on these systems and try to fit SIDs and ICDs and so on. Yes. Right. Yeah. So I think that there are two things in your comment. Just to look if there is data on that band for those systems. I mean, that's one point. Let's send information, the suggestion to Ingrid and Eduardo. And if maybe you have multi-wave band data, maybe even trying to fit SED. So if anyone is interested in doing that, that's the easiest thing of having small samples, that you can try to do a lot of things by hand, you learn, and then you try to make more automated for larger samples. So thanks for the suggestion. Yeah. Any other comment on that? I know one of the systems was like in the list to be observed by JWST. I don't know if it was observed. One of these 20, right? You found this.
Yeah, I actually found one system in in a database where you get the imaging data from space telescopes. But then I looked after for a few months and there wasn't any system there. So I'm not sure if there was a bug or something else. So not sure if it was observed by JWST or not. Not sure.
Thanks. Any other question, comments connected with these talks or not? Otherwise, to heat up a bit the discussion, we have selected some topics that maybe are maybe some people are interested in them. Then we can further discuss them down the week. But two of the topics that we selected that maybe to discuss is opportunities for strong lensing in the LSST. As we mentioned before, LSST is expected to discover about 100,000 of these strong lensing systems. This is wide field ground-based survey. So it's the kind of thing that many people have been dealing with. It's the kind of data you'll hear tomorrow from the last Beru sample. Of course, it's motivated by that. That's why the name. So yes, we wanted to hear like if people have like a specific interest in LSST or if they need to be motivated, why this is interesting. So that's one side. And the other side, which is connected but independent, the fact that everything that we said up to now is static. We have nowadays like a handful of supernovae on strongly lensed supernovae. We have a handful of multiply image quasars. And these with surveys in the time domain, especially in the case of LSST, because it combines depth, cadence, and good PSF. So we expect to discover, I think, about 1,000 strongly lensed supernova or hundreds. It's always depending on how you classify how many images, etc. But basically, it's one or more orders of magnitude increase in what we have. So we will have information on the time domain. There is, of course, a lot of effort that has been put in the time domain for QSOs. So following QSOs, light curves. Yes, in this case, it's light curves, not a rotation curve. So having QSO light curves, QSOs that have variability, and then you can measure the time delay. So this is a way of measuring the expansion rate, which there is a lot of controversy nowadays because of the seemingly inconsistency of estimates of H naught from, let's say, CMB and for lower redshift probes. So that's a total independent way of measuring H naught. And there's been a lot of effort on the time delays from QSOs. Well, supernovae, they also allow you to get time delays, but also if they are type 1As, you can compute magnifications, so you have more constraints. So that's a lot of new information that we have not been using yet, and that will be available soon with LSST. Well, so does anyone want to say anything about it? Comment about that? So next week, here at CPPF also, there will be a meeting on Think, which is a broker, which is like an interface that receives data from telescopes, especially from LSST. LSST will produce about 1 million alerts per day or per night. So everything that wasn't there before, like near Earth objects, supernova, whatever, if in the difference imaging something pops out, it will send an alert. But this is about expected, of course, 1 million per day. So what you do with that? Well, nothing, a person. But these brokers, they collect this data, they cross-match this data, they keep older data, so they allow you to make light curves. Maybe it fits like a type 1A light curve, or you can cross-match with some QSO and anyway, different brokers match the information in different ways. But the whole idea is to receive information that SST sends in a very raw way and try to classify this into something with some algorithm and then try to send back to people or to automated systems that will perhaps follow up this data. So of course, one idea is to exploit the time domain data from LSST, but a lot of the data you really want to follow up and in real time, right? If you have a supernova, you want to make a spectroscopy, to have a spectroscopic characterization, you want to do it fast so that maybe if it's a type 1, you want to determine the light curve in this case very precisely and so on and so forth. So brokers are part of the ingredient in this ecosystem of time domain stuff. And there is this Think broker, which is one of the 7 brokers of LSST. And so that's one of the things that is interesting to start thinking about. For example, as a very, very simple case study, and I think João will mention that next week probably, we cross-match supernovas discovered in the Zwicky Transients Facility, which is an ongoing project in the time domain. Very bad PSF, it's not a LSST small telescope, but already they found many supernova candidates, and then we cross-match with our strong lenses and we find matches. So maybe these are multiply image supernovae. So that's the kind of thing that you can start doing, right? So I know if people are interested on that, I think this is one of the ways forward to start looking in the time domain. There is the physics side that we discussed in the morning, like yet the time delays are sensitive to the sum of the potentials, like lensing, but to different sensitivity, not the derivative. So there is interesting physics behind, besides measuring H naught. And that's a lot of new data, not a lot of information to extract. When you make the modeling, we are using as constraints the pixel brightness distribution. But when you have time delays, you can, if you measure time delays, you can put time delays as a constraint as well. If you know magnification, because it's a type 1A supernova, you can put that as a constraint also. So you can also improve the modeling of the systems. So there's a lot of things that involve the time domain. And of course, LSST will be like the major driver of this because of the combination of wide field, depth, seeing, that will be rather unique. I think it's so unique that LSST has 8 science collaborations, and one of the 8 is strong lensing science collaboration. So this just shows like LSST is the major optical astronomy collaboration from the ground, period, I think. And the fact that there is one collaboration on strong lensing shows the importance of strong lensing in this project, right? So we want, well, yeah, I think we want to motivate people to get involved. There's a lot of ways of contributing. Of course, if you want to be member of the Strong Lensing Science Collaboration, there is a thing about membership data rights that we can discuss. But there are many, many other ways of contributing, like simulations, which don't need data rights, having data from other surveys. There are a lot of agreements that can be made for external collaborators and so on. On the time domain, there are collaborations that do not require data rights in the LSST. So yeah, I would say we can discuss this now, but if people are interested really in getting involved, we can carry one of these focus discussions on the second part of the meeting to really discuss like, okay, I want to get involved. What do I do? We can discuss that further. But so far, questions, comments?
It's a true question in the sense that it's not meant to establish a discussion, but one of the things when we're thinking about this, the organization of this meeting, we had some hands-on activities, and I thought, oh, so I have a student who's working on Illustris TNG50, and yeah, maybe we could use that. But then I couldn't get my head around how we could actually study lensing within this. And I think you mentioned there's somebody who's working on TNG here. And I mean, I'm kind of ignorant in that sense that I don't know how, because I think of lensing as a, you know, a view, you need to a line of sight. So I was wondering, is there, when you're saying that there's many other ways that we can contribute, is there a way around there? Because you say simulations, but we're not talking about TNG like simulations, right? We're talking about other ones, or so my question is more, can you clear this up for me so that I know if I want to pursue this subject or not?
We just have a microphone, but we can keep walking. That's also good. So it's great that you asked this question because it's also reminded me that I wanted to ask a question to Carlos, who is still online. So when I said simulations, I thought about simulations of strong lensing, right? So we project the light from a source to an image. But now what's the lens? Sometimes the lens is a simple model like a single isothermal ellipsoid or something. But sometimes the lens is the result of a n-body hydrodynamical simulation, for example. So when I say simulations, I do mean simulations of images, strong lensed, but the lenses can be taken from simulations, ideally, the mass distribution. And that is usually better because, of course, there is not those smooth profiles like we use in analytical profiles, but rather this clumpiness. Of course, there is a resolution issue and so on. But yes, I think there is a lot of room. This kind of thing has been done literally decades ago. So there are several papers, like 1998 papers, where they do ray tracing on n-body simulations and they produce arcs and so on. And after these decades, these things just got better and better and better. Now you can use the magnetohydrodynamical simulations. You can use brightness profiles. Well, you agree, add more degrees of realism. But this is a really hot topic. I mean, being able to do that. So I think there's a lot of room for that. But since Carlos has shown in his the beginning of his talk as a motivation, a measurement of gamma from the Illustris TNG. So maybe, Carlos, you can go back to that plot and I can ask many questions that I had. So we can go for...
Yeah, I can show you, but that gamma is not the gamma ppm. That gamma is the slope of a power law mass profile. Just to be sure if...
Sure, that's what I want.
That's what...
Yeah.
Oh, okay. Yeah, I can show you. Let me just open the presentation again and I can share.
Just to put into context, because Karim wasn't in the very morning session. So yeah, Carlos gave a talk on measuring the Poznanian parameter gamma on one galaxy, but he discussed the slope of the density profile from the PNG simulations. That's something he's working now. Right, that one.
That one, yeah.
Yeah. So can yeah. So I
don't know. Yeah, you can make your question and then I can
I have a lot
add
of very
something.
basic questions, but okay. So this is the slope of the density power law density parameter as a function of redshift derived from
Yes.
TNG simulations, right?
Yes, for TNG.
So the first, yeah.
No, go ahead.
So the first question is this gamma from a 3D fit to a power law density profile and you get gamma, so there's no lensing with that? Or is this like you simulate a lensing and then fit by a power law and you get this value of gamma?
Actually, this value is not a fit. They construct the profiles directly from the particle data in the simulation, and they measure this profile. I mean, they probably fit a power law to the density distribution that they are extracting from the TNG simulation, but it's not a fit to real data in the sense that there are no observables here. They are just picking the particle data, constructing some radial profile, and then deriving this gamma parameter. What they are trying to show with this is this two-phase evolutionary scenario that we can also see in real observations. And what they are showing here is that the simulation match what we are seeing in observations. When we actually model the lensing or dynamics.
Okay, a basic question about this plot. The yellow curve is early type galaxies, and what is the blue one?
Oh, okay. This is because they select all the samples in the TNG simulation, and they split the sample into main categories. So ETGs, they are considering galaxies that are ETGs in all the redshift beams. And the blue curve, they are considering the main progenitor branch, which are all the galaxies in the TNG simulation. And they require that these galaxies become ETGs a partir from a redshift 1. So before redshift 1s, these galaxies are not necessarily classified as ETGs, but after redshift 1, these galaxies should be ETGs. So this is the difference. And in yellow or orange here, these galaxies are classified as ATGs in the whole redshift interval that we are seeing here.
Okay, and now your work is on strong lensing of PNG, right? So for your work, you did like this 21 system.
21.
So you, in this case, you made a ray tracing on 21 galaxies from the TNG.
Yeah, we select some ETGs in these two redshift beams here, 0.05 and 0.5, because we have catalogs that already classify galaxies in these redshifts as ETGs or as late type galaxies. And then we project the particle data into a grid to simulate some surface density profile. And then we put some source galaxy at some redshift, and we retrace this source galaxy to get the lensed source. This is what we usually get from observations. But the mass profile that create these things, these observations, are derived directly from the particle data in the Lustris TNG.
Right. So you take 21 galaxies split among these two beams, so maybe 10, 11, something like that.
21. Oh no, 21 in total, but because we required some cuts, so we just select galaxies in these two redshifts, but then we need to retrace this galaxies, selecting these redshifts for redshift 0.2. Because we actually, we just using these catalogs to make a pre-selection to be sure that we are selecting ETGs. But it's not necessary that we have 10 galaxies in redshift 0.05 or in redshift 0.5. No. The idea is that we select galaxies, ETGs, in these redshifts, and then we follow these galaxies to get the particle data, or to get the results at redshift 0.2. So all of my galaxies are at redshift 0.2.
And for each lens, how many times how many images you produce? How many times do you lens the sources?
We only made one projection because we can do more, but we actually sample the angle, the inclination angle for some distribution to create some randomness in our sample. But in principle, we can choose the angle of projection and create as many observations as we want.
So was there like limitation due to computational time? Why only 21 systems and only one projection, only one lens per system?
Yeah, that's this is the why we have this like alert symbol here. Create these things is not too computationally expensive. It's actually pretty fast, I guess. But modeling these systems is very expensive because we need to apply a whole pipeline and make this self-consistent modeling, which can be really time-consuming. So this is the first thing. Why we are so few galaxies. The other thing is that TNG15 has an issue with that because many of the ATGs in this simulation is actually fast rotators, which means that they have a significant amount of rotation, even if for the ETG galaxies, which is something that we do not see in observations. I mean, we see fast rotators, but not as many as we saw in TNG. So we try to avoid these fast rotators because if the galaxy have a very high velocity, this break the Jeans assumption. So we cut these galaxies from our sample. And we also require some amount of mass because we don't want very low mass galaxies because the ascending radius will be very faint and very small, and we are not very interesting in model these systems because getting this data is very difficult. So this is one thing regarding the number of samples we have. And the other thing is that create this kind of observation here has other issues that are not related to the size of the sample, but how we create these things. Because the simulation, TNG simulation, we actually have access to the particle position and particle mass, and we need to project these things into a grid to create the surface mass profile. And in this procedure of projecting the mass, the particle mass, we introduce some noise, some Poisson noise that is really hard to solve. And actually, if anyone have suggestions to that, I'm taking, because this is something that we still don't know how to actually solve. So I'm saying this because you ask about the problems with create these data sets, and this is, I think, is the major problem. We are introducing some Poisson noise that, for my case in specific, that we require both information, lensing and kinematics, is really hard to solve because we cannot smooth out the lens observable, like applying some kernel, because we need to apply the same kernel in the to smooth the data. We need to apply the same thing in the velocity map, and we don't want to do that. So yeah, I talk a lot. Sorry.
Thank you. Comments about that?
Just a quick comment. If you're looking for something to do denoising, you can probably use some sort of autoencoder. It's a neural network based model, and it works really well for denoising. So if you're looking for something, look into it.
Yeah, this is interesting, but this will like change the profile in the mass profile in any way, or this is or not.
No, it shouldn't. If it's well trained, it shouldn't. I won't guarantee that you can get a good result, but I think it's worth a try.
Oh, okay, that's interesting. Because one of the things that people do in the literature when creating these data sets from hydrodynamical simulations, they apply some smooth particle kernel to smooth the particle distribution. But these things, in principle, change the mass distribution. And this is an issue if you require both information, lensing and kinematics. But if you are only interested in the mass distribution, we can smooth out. It's not a real problem as far as you consider this later in your modeling. But it's good to see that, to know that there's an option that I can remove this noise without changing the profile. Thank you.
Yeah, so I think there is a lot of room for those interested in the interface between using high resolution simulations and making them lensing there forward and modeling them back like Carlos did, right? Yeah, I think there's a lot of interest in that. I understand that in your case, Carlos, you had in mind like IFU data and HST image, but perhaps it's interesting also to look like in a coarse grained like LSST imaging and maybe IFU, but like NIFs or SIFs, like smaller IFUs, not MUs, but smaller ones. Maybe you have less spexels per system. You went down to 15, maybe going down to, I don't know, 10, 6. What I think it's a regime that where we may have a lot of data, right? Muse still is one single instrument, but there are a lot of IFUs smaller that that we may have data. So I know it's a lot of work. It's already very interesting what you did, but I would be very curious to try to see what your results map in the case of ground-based imaging and lower spexels, let's say, lower resolution IFU.
Yeah, it's completely possible because the way we write the code, it's very way to change the inputs and just telling the code that how resolution you want to get and how the number of kinematical beings. So creating this data set is not very difficult and neither time consuming. The problem is just modeling these the data sets before we get them. This is the time consuming part. But yeah, it would be interesting if anyone has like time and machines to do this. I'll be very glad to create the data sets and help with anything else.
Cool. Any other comments, questions, suggestions? Okay, I think today has been a tough day, so people are getting tired. So we have a lot to discuss in the upcoming days. Perhaps it's good to close here. We see everyone back tomorrow at 9 a.m. Tomorrow is just half a day. Then enjoy the holiday on Wednesday. Then we are back on Thursday, the full day, with a lot of hands-on. And then Friday, we have a lot of time for discussions too. So yes, thanks for participating, both remote, in person. See you tomorrow. Yeah, thanks all speakers. Yuri has a question or just clapping? I think people are just clapping. Yeah. All right. Bye-bye. Yeah.